from Stellenbosch University, and he'll be opening up our eyes to the challenges and opportunities that face building a quantum-ready Africa. So let's hand it over to Francesco. Thank you.
Yeah, thank you very much for the introduction. And it's really nice to see that we have a quantum computing session at the CHPC. You know, back in 2007, I was the very first South African research chair in quantum information processing and communication, and nobody knew what I was talking about. So it's really very nice to see that things are getting institutionalized. Yeah? That's really fantastic. Okay, in the next half an hour or so, I will try to give you a little bit of an overview in the introduction. I will remind maybe some of you on the quantum beginnings, yeah, just to put you in the right mood. Yeah. I will mention some of the achievements of the so-called second quantum revolution and why it is relevant for the fourth, and some people already speak of the fifth industrial revolution. Yeah? And I will conclude by describing why we can't miss this opportunity and some of the challenges. And I hope that the ratio challenge to opportunity will be 20/80. Yeah, like the previous keynote speaker addressed and suggested. So, you're all familiar with this, yeah? With the exponential growth in computing capabilities. On the left is the 4 or 5 points that Gordon Moore fitted to extrapolate his famous law, yeah? And now we are at, I don't know how many billions of transistors that we have on our chips. Yeah? This goes, of course, parallel in the speed, yeah, of our computers. The price luckily went in the other direction, yeah, which is very good. Yeah. And these days with, you know, everybody uses CHPC, but it comes at a cost. Yeah, there's a lot of computing power behind it. And that's why we need lots of GPUs. And it was very nice to hear that our CHPC is upgrading the GPU pool. That's fantastic news. Yeah, but that comes with a problem, yeah, and that's electricity consumption. Yeah, if you look at all data centers in the world there are very few nations that consume and produce more electricity than the data centers in this world. Yeah, so it's really important to start looking also from a purely energy production point of view to see if there are alternatives to this very intensive computing needs. Yeah? So what options do we have? Yeah, traditional computers, let's call them classical for our purposes here. Bits are just mathematics and information. Yeah? We have two other options to look for alternatives. One is to go the biology route, yeah, and try to model with a neuromorphic kind of approach what our brain is working, yeah? Although we don't know exactly how that works yet. Yeah? The other route is to go the physics and information route, yeah? And that's where the coupling of quantum physics with information comes in. Yeah? And it goes back almost 50 years, more than 40 years, that Richard Feynman had the intuition that because we know that nature at the fundamental level is quantum, if we had some kind of quantum machine, it might be a good idea to try to simulate nature using quantum machines. Yeah? And let me show you now the worst case scenario. Yeah? And the worst case scenario for this quantum computing business is that we will have some kind of quantum device that is again specialized to solve some specific problems in a more generic high performance computing architecture. Yeah? And we know, for instance, that quantum devices are good at estimating kernels for AI, for instance. Yeah? So the worst case scenario could be that we have just a little quantum FPGA or something like that solves that particular problem. Yeah? The ideal case is, of course, that we have a universal QPU that does everything we want it to do. Yeah. Quantum computing development, at the moment, we are somewhere in the middle, in this NISQ era of noisy intermediate state quantum computing. Thank you very much. I just brought one. Thank you. Yeah, where we don't have enough qubits, which is a quantum version of the bit, to implement error correction, and we hope to, in the near future, to have lots of logical qubits that are error-free, that allow us to do exactly the universal quantum computing that we want. Yeah? And there are some indications that we did specifically in this year huge progress in that respect. I will mention it probably later. Yeah? At the moment, we have around 1,000 qubits. That's what we have. Yeah? Noisy qubits. The logical qubits machines that we have, or some people have, not we, have around 20, 28 logical qubits. People reported 40 logical qubits, and that is really a very exciting development. Yeah? There are many technologies proposed to build quantum machines, from superconducting to photonics. Each of them have advantages, each of them have challenges. Yeah? And I wouldn't want to put all my money just on one technology. Yeah? It's probably still fairly open which technology will win, will at the end. So it all started, and I introduced this slide because just 100 years ago, Louis de Broglie came up with his theory that the fundamental particles, like electrons, have also wave character. Yeah? So that was just 100 years ago. So this was celebrated this year. That was his PhD thesis in 23. That was then published in 24. Yeah? And that was celebrated this year. Yeah? Other people I mentioned before, like Richard Feynman, and he denoted still this mystery of particles behaving like particles and like wave as one of the fundamental mysteries of quantum physics, and it's just a matter of getting used to it. Yeah? But that's how it is. Yeah? I just wanted maybe to introduce an educational component. Yeah? This is all you need to know about quantum mechanics. Yeah? The fundamental quantity of quantum mechanics is something called the probability amplitude, yeah? And it's essentially the square root of a probability. Yeah? And the two rules are simple. If something happens in a sequence, you multiply these amplitudes. If something happens along different paths, yeah, you just add them, and the probability is always the square. Yeah, so this is essentially the basic of quantum mechanics that you need to know for quantum computing. The other interesting aspect is the superposition principle. Yeah, you all heard of these paradoxical examples of cats that are dead and alive, and that's something that our classical bits can't do. And people got in trouble for this. And then there is, of course, the next, even less intuitive property of quantum mechanics that was rewarded with a Nobel Prize a few years ago, yeah, which is entanglement. Yeah, the property, the really intrinsically non-local property of quantum physics. Yeah, objects that are entangled, even if they're very, very far apart, are very strongly correlated, much stronger than any classical correlation could do. Yeah? And this is one of the resources that classical computers don't have. Yeah? And in quantum computing, you use it to actually do things. Sorry. Yeah? So the first quantum revolution, started at the beginning of the 1900s, yeah, with Planck and Einstein. Then I mentioned de Broglie, and soon afterwards Schrödinger came up with the equation that describes the quantum phenomena. And then it took another 20 years or 30 years until the really first interesting applications were built. That's the transistors just after the Second World War, LEDs, lasers. Yeah? So it took a long period, yeah, from the 20s to the 60s until the first really applications of quantum mechanics took on. Yeah? And this also, this split, yeah, from the original formulation to the application is also the step from the first quantum revolution to the third industrial revolution. Yeah? So quantum physics was really fundamental for us experiencing the third quantum revolution, the third industrial revolution. Yeah? So, but then in the 80s something happened, yeah? that led to what we call now the second quantum revolution. Yeah? And that was that for the first part, and I'm cutting the story a little bit short because there are many other things that I want to mention, yeah? Where we were experimentally able to manipulate single quantum objects. Yeah? It was only in the 80s that we could trap a single ion or a single neutral atom or a single photon. Yeah? We couldn't do it before then. So from the 20s to the 80s, speaking of quantum particles was just imagination. Yeah? We only could do experiment in bulk, not on single quantum particles. Yeah? And that's when the business started, with Feynman coming up with the idea that maybe one day we could have quantum computers. And quantum information processing is exactly the storing, processing, and communication of information exclusively using quantum physics. Yeah? And this is what happened at the end of the last century. Yeah? Quantum mechanics and information science came together, forming, some people call it quantum information science, with the three major pillars of computing, communication, and metrology, with the final aim of maybe one day having a fully fledged quantum internet. Yeah? So quantum metrology or sensing gives us very precise measurement. For instance, gravitational wave we couldn't measure if we didn't have quantum sensing. Yeah? Quantum communication promises very safe data transportation based on laws of physics and not on mathematical complexity, and quantum computing is what we are going to speak about now. Yeah? Just for those of you that maybe not so familiar with these things, the transition from the classical bit to the quantum bit can be very simple. Yeah? The classical bit, just think of a switch, current is on and off, 0 and 1. The quantum bit, we need a quantization procedure. Yeah? And the idea is to identify the quantum zero state, yeah, which is in these fancy angular brackets that are called Dirac brackets, as a two-dimensional vector. So the 0 is at the top, the 1 is at the bottom of a sphere. Yeah? And because of the superposition principle, because quantum mechanics lives in a complex space, you can represent this qubit as a vector pointing from the center of a sphere to the surface of the sphere. Yeah? And every point on the surface of the sphere is a legal qubit state. Yeah? And this sort of explains intuitively that there's a very different way of processing information going on here. Yeah? So I mentioned quantum computing, the first idea were in the 80s. Yeah? In the mid-80s, David Deutsch in Oxford did what Turing did for the classical computer. Yeah? He showed that in principle it is possible to design a machine that manipulates information completely quantumly, yeah? In a completely theoretical way. Yeah? Then nothing happened for a long time, until in the mid-90s, Peter Shaw came up with two very important algorithms. Yeah? He showed that if we had such a quantum machine, yeah, there is an algorithm that allows us to factorize into prime numbers, yeah, in a way that is, from a complexity theory point of view, more efficient than what classical algorithms can do. Yeah? And that was the first example of something useful that such a machine could do. Yeah? The same Peter Shaw came also up with an algorithm to do quantum error correction. Yeah? And this was really the momentum that after the 16%, yeah, that quantum computing needed to kick off. Yeah? Because we knew all of a sudden they can do useful things and not just some play algorithms that were known before then, yeah? Could do something really useful. And if we were to build such a machine, we know in principle how to make them error-free. Yeah? So and that kick-started a lot of interest. Many algorithms were developed, and so on and so forth. Yeah? And the first experimental quantum computing experiment with just 2 qubits at the end of the 90s was done with NMR technology, yeah? As a proof of concept. And then in the, sorry, I don't have it on this slide. Sorry, in 2019, so I don't remember the year in which IBM put its first quantum computer in the cloud, but it was not so long ago. Yeah? In 2019, Google thought that they had proven quantum supremacy. Yeah, and this, again, couples a little bit with the, let's say if the second quantum revolution started in the 80s, yeah, we know that in the 2000s, the fourth industrial revolution started. Yeah, so there is really the momentum, again, of quantum physics to kickstart another revolution. And now in the 2020s, yeah, we know we are already in the fifth industrial revolution, yeah, in the era of CHPC and so on and so forth. Yeah. So quantum computing works a little bit like classical computing. Yeah? You have certain algorithmic primitives that you can put together to do useful things. Yeah? But I don't want to bother you with technicality. Let's see why this all matters for us. Yeah? This is a recent slide of 2024 that shows the national governmental investments in quantum computing across the globe. Yeah? And you see, China has already invested $15 billion. Yeah? Our $3 million are just a drop in the ocean. Yeah? Europe has invested a lot, US, Canada, many countries. So it's really taking over the world, yeah? The interest for quantum computing and the potential for economic development. Yeah? Australia, after this slide was done, invested $1 billion Australian in additional attracting quantum computing hardware companies to Australia. Yeah, so there are really big hopes, and they are attached to serious funding. Yeah? There is also a lot of private funding. Yeah? What the Googles, Microsoft, Intels of this world invest, I don't really know, but it's certainly similar amounts. Yeah? Why are the opportunities for Africa? Yeah? The main reason is, of course, that Africa is a young continent. Yeah? And young people love new technologies. Yeah? So we need to get our young people to love the new quantum technology. Yeah? Because we have the opportunity really to leapfrog into this second quantum revolution and the fourth and fifth industrial revolution. One serious mistake that the whole of Africa did was that it didn't invest in semiconductors. There is not really any notable semiconductor facility on the African continent. Yeah? And other countries like South Korea lifted themselves up from probably even worse conditions than we were in, yeah? to the status that they have now. Yeah? And now we have, again, two great opportunities, yeah? AI and quantum technologies. Yeah? If we miss both those trains, we will be in trouble again for another 50 years, probably. Yeah? So it's really critical that we do what we have to do. Yeah? And also, we have our own specific problems, so we can also come up with our own local innovations and so on and so forth. But this is probably one of the major arguments why we need to get involved. Yeah? In Africa, like in many other parts of the country, yeah, we are facing really complex challenges, yeah, from climate change to food security, diseases, energy, and so on and so forth. Yeah? And all these problems, yeah, are really complex. Yeah? There are huge data sets involved. There are huge intricacies. Yeah? And the hope is that quantum computing might be able to assist in addressing the modeling of some of these issues. Yeah? For instance, climate change is something, this is out of a local, recently published book, yeah, is affecting us badly. Yeah? So we really need to improve our abilities. Yeah? And it starts long before quantum computing, because we don't even have a Southern African climate change model. Yeah? We need to develop that as well before we can go the AI and quantum route. Yeah? And this is something that NITEX, our National Institute for Theoretical and Computational Sciences, is trying to do. Yeah? Recently, Mark Nazila, who is the Chief Risk Officer of R&B, published this very nice book on African artificial intelligence, where he really lists, it's a very thick book, all the possible uses of AI to uplift not only South Africa, but the whole African continent. Yeah? We hope to do the same using machine learning on quantum computers, but that's probably the topic of a different talk. You know, what are the use cases? Some of the use cases where quantum computers can be worthwhile. Yeah? Mainly, it's simulation use cases, and I will explain later why. Yeah? So, for instance, the development of new materials for carbon capture, yeah? It's a complicated problem. And if you can manage to simulate it using quantum hardware, that would be really very good. Yeah? Other examples like tackling antibiotics in wastewater. Yeah? It's also a very difficult problem to address numerically. Yeah? And just some examples. Yeah? Fertilizer production, yeah, it's really critical. Yeah? You know, to produce artificially fertilizer is a very complicated and costly procedure because you need high temperatures and high pressure. Yeah? But bacteria outside the exhibition center in the ground do it for free, but we don't know how they do it. Yeah? So we need to develop models and solve them and try to understand how we can compete with more natural fertilizers. That will help us address many of the issues that we have. Yeah? You know, we all went through COVID. Yeah? We know that vaccine production, distribution is a very complex problem. Yeah? So that also one of the use cases of future quantum computing as an example. Yeah? This is also a very interesting one. Yeah? We need to make sure that our food production is sustainable and nutritious. Yeah? We want everybody to have enough calories, enough vitamins, enough everything. Yeah? Yeah? But it's all coupled to climate change these days. Yeah? So some crops that grew somewhere don't grow there anymore. Yeah? So to model this ecosystem of food production is really, really very complicated. Yeah? And I've been involved with GESDA, which is the Geneva Science and Diplomacy Anticipator, and the Open Quantum Institute at CERN, to try to develop models that could run on a quantum computer, or that should run on the quantum computer that we have access to now, yeah, and see that that we can contribute to this kind of problems. So, what do we need to do? I mean, it's all fairly obvious. Yeah. First of all, we need to do what we are doing here now, yeah, and what we were doing yesterday in the workshop, which is educational awareness. Yeah, we need to train young people and maybe not so young people, yeah, in the use of quantum computers. Yeah. We have partnered with QWorld, yeah, that is a non-governmental, non-profit organization, a little bit like the carpentries for Python and data science, with explicit aim to teach and share quantum computing knowledge. Huh? And in fact, this week we are running the so-called Q-Bronze course online with hundreds of people from all over Africa, yeah? that teaches the basic of quantum computing. And then, of course, there is Q-Silver, Q-Gold, and Q-whatever, yeah? as we go on. Yeah? So that is the one thing. The second thing that we are doing right, yeah, is that in our South African quantum technology roadmap, we decided that it will be the CHPC that provides us with access to quantum computing hardware. Yeah? And that is a very, very, very nice partnership, so that we don't have to worry about buying our own quantum hardware. Yeah? The CHPC will do it for us. Yeah? So that is very good. Yeah? We have also, in South Africa, an important international partnership, for example, with the Open Quantum Institute, yeah, thank you, that is based at CERN in Geneva, which was created as an institute to give access to quantum computing worldwide. Yeah? And then, luckily, funding and policy, It took us a long time, but eventually, since a couple of years, we have a South African Quantum Technology Initiative, which followed a quantum technology roadmap for the country, yeah? And that gives us some kind of policy framework locally in which to operate. Yeah? So this is very good. So what are the challenges? The challenges is really the fundamental challenge, and that is a challenge to the scientists, yeah, to the quantum computing crowd, yeah, really to show that there is quantum practicality, that we can really use quantum computers to solve problems that are interesting. Yeah? You know, we know on paper that certain problems can have an exponential speed up, yeah, if you increase the size of the system. Yeah? Google, I told you, 2019 claimed they had quantum supremacy in the sense that they claimed to have solved a problem in a few seconds that would take another high-performance computer hundreds of years, yeah? But then a few months later, people solve it classically more or less in the same time. Yeah? So, you know, there is a healthy competition. Yeah? You claim something and then others do it better using traditional hardware. Yeah? So the problem is to find meaningful application and show that it works. Yeah? And there is I put a reference here, a very interesting paper of last year by Matthias Troyer, who is the quantum guru at Microsoft, and some of his colleagues, where they did this very interesting experiment, yeah? Or this very interesting study. Yeah? They compared what a single NVIDIA GPU can do, yeah? Investment $10,000, more or less, yeah? With what a hypothetical quantum computer, yeah? With 1,000 logical qubits. At the moment, we have 1,000 physical qubits that are not error corrected. Yeah? So this is something that we will have in a few years from now, yeah? Yeah? With certain very good parameters for the time of the gate operation, for the architecture, and so on and so forth. Yeah? And, and they quickly came up with a bottleneck. Yeah? You see, for instance, I started mentioning AI and so on and so forth, yeah, which has huge data sets. Yeah? But if you want to manipulate a huge data set on a quantum computer, the first step is that you need to convert the classical data, yeah, your data set, into a quantum state. Yeah? And that is a slow operation. Yeah? So, and the difference is in a GPU you can read and output data at 10,000 gigabits per second. Now, on this fantastic quantum machine that we don't have, it's probably 10,000 times faster. Yeah? So if you have billions of data points, yeah, to input them on a quantum computer, it will take you billions times 10,000, yeah? Slower than what you can do on a GPU or on the 36 GPUs that we will soon get. Yeah? So that at the moment, yeah, with the hardware that we have now, and probably in the near future, yeah, we should really not focus on solving problems that involve big data sets. Yeah? So the message for us, and that was aligns with the test, with the examples that I mentioned before. Yeah? Quantum computers are just practical for compute problems. You have few data, but lots of computing is necessary. Yeah? Typical example, if you want to simulate some chemical system, yeah? You have just a limited data set, the parameters of your molecule, and you want to find the ground state of that molecule, would be a typical application. Yeah? Yeah? And so that those are the problems where we can expect to see our exponential speed up. Yeah? The reason is shown here. Yeah? You know, if it takes you 2 weeks to input data on a quantum computer, whatever speed up you have that is not exponential is easily lost. Yeah? So if you don't really find problems with exponential speed up, it's more or less hopeless. Yeah? We have a lot of catch up to do, yeah? Because just as an example, yeah? Amazon and Microsoft have in their cloud let's say around 5 different quantum computers that they own. Now, at the moment, we don't own one. Yeah, this is one of my last slides. Yeah, the UK Quantum Computing Center has a dozen different quantum computers of different sizes in their in their computing center. Yeah? So we have really a lot to catch up. Yeah? Yeah? A problem that we might have, yeah, that came up very recently, yeah, is that some countries like the US and the UK, they're starting thinking about export controls for this kind of equipment. Yeah? So maybe at some stage we'll have to think about building our own, yeah, if things go wrong. Yeah? A few months ago, I was asked to give a talk at the Science Summit around the UN General Assembly, and the title of the session was Africa Rising. Yeah? And I tried in a little bit of a playful way to quantify the factor that we have to rise. Yeah? At the moment, our CHPC has a cluster with 30 GPUs, yeah? I think. Yeah? A national laboratory in the US, one chosen at random, yeah, has clusters with around 30,000. Yeah? So we have a factor 1,000, a factor 1,000 to go. Yeah? Not considering that Elon Musk buys 100,000 when he wakes up for breakfast. Yeah? And is buying more. And I don't know how many GPUs Microsoft and Google have. Yeah? It's probably in the millions. Yeah? So we really have to catch up in this area, and of course in the quantum computing area as well. Yeah? One thing that as NITEX we try to promote, yeah, is, and it's all related. Yeah? I mentioned as an example climate change. The computing power is not the only problem that we have. The other problem that we have is that we don't have enough data collection stations. Yeah? There are very few data collection stations relevant for climate change across the African continent. Yeah? And one of the things that we did a little preliminary study is that by using the infrastructure of the SKA, one could deploy a network of data station, essentially satellite ground station, coupled with other data collection center, coupled with local high-performance computing power, yeah? All networked together. And, and a very rough preliminary study shows that it could even be a self-sustainable project, yeah? Because there are lots of industries, agriculture, banks, insurances that would be keen to buy this data, yeah? And have them processed for themselves. Yeah? So there are scenarios where working together between industry, government, and academia, we could really dramatically increase our computational ability and modeling capabilities. Classically and quantumly, you could probably do something similar. Yeah? So that's it. Thank you very much. If you have questions.
Colleagues, if you could please save your questions for the end, then we'll take all the questions to all the speakers at one go. But Francesco from Nikki's, we would just like to offer you a small token of appreciation for your contributions in quantum computing and your partnerships with NITEX and the summer school. Thank you, Francesco.
Thank you very much. Thank you.
Thank you.
Thank you very much. Sorry, I need to.
Thank you, Francesco.
Thank you.
The timing's so different. I don't know who's next.
Did you help correcting it? Should be okay.
So would help to turn it the right way around, I guess. Yeah, here we go. Here's my face.
HDMI.
Has all of them.
Do you have any sound? Audio?
Sorry?
Do you have any audio?
No. Strange.
If project the projector. Where to project it to? Extend, duplicate.
There?
Oh, there it is.
Okay.
Would you like to play?
Brilliant. Not sure if this thing's working now. What they've done. Okay, got it working. Right, thank you for inviting me to give this talk. It's a good honour. What I'm going to talk about today is the new approach to a D-Wave for obtaining thermodynamic properties of a solid solution. Before I go there, my background really is on classical computers. I'm sat in front of, on the left-hand corner there, in front of Archer, with the national supercomputer in the UK. It was predecessor to Archer 2, where I'm standing looking a little bit older with my orange coat. And I also look after a Tier 2 centre, which is a local level, I guess, supercomputer here on the right-hand side. Or, yeah, right-hand side to what you're looking at. What I'm going to talk about is the work done by 3 of my group members, Unq, Bruno and Lexi. But I start first by giving a motivation, what sort of thing I'm actually interested in. I'm interested in doing structure prediction, where I'm generating atomic structures and I'm evaluating them to see which is the lower energy configuration. And the challenge here really is to reduce the number of configurations I'm going to look at and the cost to actually evaluate which one is more expensive to the other. So I started this sort of plot back in the sort of late 1990s, where I was asked to try and reproduce what was going on by my predecessor in Richard Catlow's group, and he managed to do a genetic algorithm to solve this structure here, and that's his cost function here. And I've literally put that into a code called Gulp and started predicting structures like this. You can see what I've done here. I've got a very cheap energy function, and I'm also reducing the search space by predicting things on a grid. So it's not a continuous space, but you can quite easily resolve this by doing local optimization. Whoops. To get your structure, which is just rock salt structures here, the left and the right. But what I'm interested in today is looking at solid solutions, where we happen to know, for example, end members, and what happens when you mix these. They form various different compounds, and you want to see what happens to the properties. So down here, we might know the fractional quartz of the calcium and the strontium, but once you have a mix, there's a pattern. And the larger the size supercell you have, the more patterns there are, and you really want to know what's the lowest energy configurations. And these things are important because they are used in very many different technologies, shown down here on the bottom right-hand side. And the work I'm going to show you in terms of trying to get these configurations out is the work done by Bruno using a quantum annealer, and I'll come on to that in a second. So traditionally, to model these things, you might use the smallest unit cell and do averaging. So that if you have 50% of that, 50% of this kind of atom, you might have some sort of pink atom. Or you could try and do the one mass fantastic sort of supercell. You try to do as big as possible and do one sort of different sort of spread of configurations. Or you might try and do an ensemble to every single combination and create your partition function and go that way. What we try and do is somewhere in between. We try and go for as big as we can and do as many configurations as possible until things converge. And I'll show you how that's done in a second. Next slide. Here we go. So this is the work of Unq. Unq here is looking at this material here as manganese oxide. The manganese are in these octahedra, and he's looking at trying to reproduce the experimental data shown here, that this is a cathode material and lithiums go into this material. The voltage will change. Depending how much lithium you have in this system. And what he first has done is try to predict where the lithiums go and which one of these manganese 4 becomes manganese 3. And he's done various different occupations of this thing here and got his prediction. And looking at this, he can then look, this is the DFT result earlier, he now has this prediction here of how the voltage changes. And from this, we can work out what's happening with this straight line. Why does it drop suddenly? You can see that the lithiums like to go initially on these tetrahedral sites, and then when you've got them all full, they then push these lithiums that are already there to go sitting on the octahedral side. And that costs energy, and so that's where the voltage sort of drops quite dramatically. But of course, this all happens at temperature. And these are all calculated initially at athermal conditions, and once you start looking at temperature, you need to know what the lower energy states are. And so by randomly putting lithiums on these sites and relaxing them and changing the configurations of the manganese 4, you can see if it does 100 samples and gradually increases the sample, the number of states then begin to converge. And so we go, okay, well, by this stage, we know we've now represented the actual true nature of this system. And of course, you have to do this for various different concentration of lithium, and you can see that this peak here begins to move to the left as you add more and more lithium and begin to split, and we can then try and interpret what's going on there. But essentially now we have this occupation down here. We can now change our system and use the Boltzmann weighted distribution, and we can now see that our prediction is this line here, and it's much more similar to that was seen, observed in nature. And the reason why it's slightly to the left is because, of course, we have a perfect system, and nature will have lots of crystals with sort of boundaries, and these boundaries where the lithiums can actually go first before they start occupying these channels, so on and so forth. So that's the classical way, where we have to do many, many different configurations. And what we'd like to do is use a quantum annealer to find these configurations down here, the patterns here, and where the lithiums go. Okay, without actually having to sample all these other ones that are not relevant to the temperature we're looking at. So what we're going to try is use this D wave, and the D wave, in my mind, the way this works, helps me to think about what's going on here, is we have these qubits, and these qubits and the interactions of these qubits are controlled by these magnetic strengths, and so you can try and somehow map your system onto these qubits and use the magnetic strengths to represent the energy and the interaction of my particles in my system. So this work is really part of the project called QVEC, and this is the team of QVEC, and like I said before, Bruno here has done most of the work, and here's 2 quantum computers that we have, these guys here have designed and started working on. But I'm not going to be talking about this stuff here, but more this D wave on the left-hand side. So what I'm going to try and do, I'm going to use, I should explain what the D-wave does. It basically does annealing. So you have these qubits, they start off randomly, you do your annealing and gives you the ground state. So rather than using simulated annealing, we're using nature's way of annealing to actually get the lowest energy configuration. So what I did last year, I came and gave this talk, I showed the initial test system, and the initial test system here was we were going to try and find, what is the pattern, the lowest energy pattern for having so many vacancies in a graphene sheet. And in this case here, you see quite quickly that if you've got 2 vacancies, they like to cluster together. The way we do this using just a smaller unit cell, just to explain the maths here, is we number all our sites in a unit cell, and each site is associated with a particular qubit. And then we need to also include the energy contribution, and it seems that the largest or the most complex term you can have in your energy expression is the so-called QUBO model. And so in the case what we're doing here, these interactions, the QIJs, which is mapped here, it's -1 if this guy is next to something, and if there's nothing next to it, then it's a 0. So therefore, the QUBO model is saying that it likes connectivity, and that's how we're modeling it onto the system. And you run your D wave, and it produces noughts and ones, and a naught represents where there's a vacancy, and a 1 represents where there's a carbon in the system. And so you can run this, and for example, you have 3 vacancies, you can see quite quickly it'll predict that the number of broken bonds is the key thing here, and if you can minimize that, then you can actually minimize the overall energy. So how does that work in principle? What's happening behind the scenes? Well, essentially what's happening is, because of the annealing process, doesn't always find the ground state. You have to run it many, many times. And in this case here, you can see we're running it 1,000 times, and it produces what the qubits are whether up or down. And you can see sometimes you get, well, in fact, in this case, 52 occasions, we're finding that every one of them wants to be occupied, which is no surprise. But we actually set this to find at least 1 vacancy, and there's lots of them down here with just 1 vacancy. Of course, they're all equivalent. And because they're equivalent, we can join those together, and you can see that 73% of the time it's actually predicting the answer we're looking for. The lowest energy configuration where there's just 1 vacancy. And we're coming in. But what I want to do is explain how this process works. So what you have over here, we have a system. We look at how the system is mapped in terms of connectivity. So every atom site needs to know about its neighboring site. So that's your connectivity tree. And then when you map this onto the D wave, and I don't think you can quite see from the back, but on the D wave here, each one of these little circles here is one of your qubits, or mapping this how they interact. So that's that thing that sits there, we mapped onto that, the hard wave, the D wave, shown on like so. Now if we want to have a penalty to actually work out the right number of vacancies, then unfortunately we also need now every atom to know about every other atom. Otherwise it doesn't know whether it's got the right number of vacancies. So now our connectivity of the system has a lot more points. So a lot more connections to the system. And because of that, we map this onto the D wave. Because this guy here needs to know a lot more connectivity, there are not enough qubits next to it for us to actually map them properly. So now we have to have several, so you can see the different colour coded. There's like blue with grey lines. We now have to have 3 qubits representing one site, so there's enough connectivity between them to actually map this guy to everything else. And the ones that are actually representing 1 qubit, so 3 of them, the magnetics tend to be stronger to make sure that they all say the same results. If they don't, we have what is called a broken chain. Okay, so if 3 of them says there's occupied, then it's occupied, but if 1 says it's down, then what does that really mean? So that's broken chains. We don't really like broken chains. But the problem here now demonstrates why it doesn't scale well. Because for this whole system here, before I just wanted that many qubits, but because of the connectivity, we need a lot more qubits in the system to be able to represent that system. So connectivity is a problem here for the D wave. So does it work? I showed this last year. Basically, you can actually predict stuff. I'm going to go very quickly here. You can predict the right combination, but when you relax the system, of course, you do get movement of atoms. So this one here, though it's predicted further down, it shows the depth in the wrong place. This, in fact, is relaxed with this structure here. So it shows that the D wave can make predictions, but based on single point calculations rather than relaxed structures. So the new stuff, hopefully I'm okay on time. The new stuff, how can we now go forward and do some thermodynamics? And the systems we're looking at here, we've got this one over here, which is nitrogen doped graphene. We're looking at aluminium to gallium nitride, and here is an alloy, tantalum tungsten. So we're going to try and model these systems here and see if we can introduce the idea of temperature. So this is the workflow. You have your end member where you know the structure, and then you can generate a supercell, and the larger the supercell, of course, the more patterns you can model in the system. And of course, then you have to map onto this QUBO model. And these things here, rather than just using -1 for nearest neighbors, we actually want to introduce proper values for these Qs. So you have very, very different configurations, and we take a number of these, not all of them, we take a sample of these and start running ab initio calculations to get your DFT energies. And we're actually calculating these things here, which is the energy of these systems minus the end members of how much you've got of them. And from those, we're putting that to somehow map and calculate the values of our QIIs and QIJs. And their vectors are x1s and xi. Xi's becoming 0 means we got one of them being aluminium, for example, and if it's 1, it's gallium, or if it's nitrogen or carbon, depending which system we're looking at. So this is what we're trying to minimize in order to get the values of our QIs and Js. So once you've got that, what you suddenly discover that, in fact, if you do this stuff here will be lower in energy than having one of them and 2 of them, etc. And you can see here's the states. If you've just got a pure system, 1 dope, 2 dope, 3 dopes, 4 dope, there's lots of lines here because there's lots of different patterns. There's only one pattern here. But essentially, if you chuck this into the quantum computer, it's going to always come out and tell you it's this guy down here. And that's not what we want. We want to be able to say, I want to predict the pattern, the lowest energy structure in this set here. And so you have to somehow bias the system. So we want to actually return not non-trivial stuff. We want the answers up here, not this guy down here all the time. And so normally you'd apply a constraint. 5 minutes should be fine. And this requires a fully connected QUBO model, and the fellow QUBO model gets long qubit chains, and that's a problem. So what we're doing instead, we had the chemical potential to try and bias the system up here. And you can see we had the chemical potential. Then the system here, when you increase the chemical potential, you can then change for this being the lowest state to the guy in here when you've got some doping. Or if you go to the extreme, you go further and further and bias the system to find the lower energy stuff where you have the amount of dopant into your system. And again, I've already mentioned this. Of course, that means, say, rather than having this situation, this situation here, going from many connections to this, we can reduce the number of qubits we need. And this just shows you how it scales. So rather than have these long chains and needing lots of qubits, we can reduce the number of qubits we need to order to model the system we're interested in, larger system sizes. So this shows what's happening. This is the carbon doped with nitrogen, and you can see that as we increase the chemical potential, we can increase or decrease the number of nitrogen in the system. And here's our results showing this way. As we increase the number of nitrogen, you can see the spread, and it looked like Gaussian distributions. So we believe that these distributions look like Gaussian distributions, and we can use that somehow to model and predict the guys towards the end here and know what configurations we want to put into our quantum mechanical calculations. But of course, as it's mapped on hardware, one of the things we also notice that when you put your system into your QUBO, into your D-Wave, the first thing the hardware does, it has this alpha parameter to spread out these energy levels, so it's more likely to find the ground state. Because there's noise in the system, you want to spread these energy out so you're more likely to find the lowest energy state. But this alpha parameter you can play with, of course. And if you play with it, you can crush these down, and that's like stretching and crushing them. It's like changing the temperature. The more you spread them out, the less likely you're going to populate the higher ones. The more you compress them, the more likely you are to occupy them. So we're now wondering whether we can use this alpha parameter to set the simulated temperature of our system. And you can see what's happening here. Change the alpha, then you see these states up here, which are higher energy, becomes lower down and more accessible to nature when you're doing a Boltzmann distribution. So does this work? Again, same situation, we change the alpha particle, you see we get this different spread in our states. This is my final result page, so relax, this is it almost. So this is the results, as we change the chemical potential this way, and we change the temperature that with the alpha thing. What I'm showing here is this colour is our D-Wave results, and the blue is the classic. And you can see that line on the top here, brown and blue look as if they're on top of each other. So we're able to produce the same results as the quantum dealer. It's slightly out at this end, extreme. I was told by Bruno that again the wrong picture is better than that. It's nice to get a blue result, but apparently the results down here and here look very similar. The quantum dealer is giving us, predicting us the right configurations. Which means that we can just then pick out the configuration we want. So in our data flow, which is the same results, now that we've done some of the calculations, we've done the quantum dealer, we find the multiple state, find states we actually want, and just do those as using ab initio calculations. And here's the two systems we're looking at. Here's the results. We now know which configuration to use in DFT. We can then do the calculations, not worry about the higher energy ones. And here are results. And for example, just looking at this one down here, this is just looking at how the bandgap goes. We can compare that to experiments. And our results here look very similar to that's coming out of experiments. So hopefully that's convinced you that we can, in principle, use a D-Wave to start doing thermodynamics. And that just leads me to put some advertisement of what other stuff we're doing in the group. In the wider group, we involve many people up here who talk also in other sessions. I hope you go and see that. It's all to do with this thing called Excalibur, which is us trying to prepare for the arrival of exascale computers in the UK, where you're doing 10 to 18 calculators per second. So this is just a little advertisement showing what we're trying to do to prepare for that by training people and software to make sure that particle-based simulations can scale onto a supercomputer that's exascale. But who knows when we'll get that in the UK. I think the budget was, sorry? They got a long way, yes. We are changing government and a change of budgets. Well, that's a change. Anyway, thanks for your time. I hope I'm on time. But I'll stop there. Do you need a machine?
Yes, okay.
That one there, okay. Let's pull that one out.
I didn't know they were that practical, those D-Waves. I've heard of them. That's very interesting.
Well, rather than doing the quantum gates,
Yeah,
we're
have you been talking to Continuum? Another interesting one. The quantum one.
chat afterwards.
Yeah.
Concentrate.
Yeah. Okay, I think our third quantum speaker is in superposition somewhere else. So they asked me to come talk about something not quantum. Okay, it's not showing. That's you.
Okay, that's that, and just.
There you go. Let's go.
Okay, good.
Okay, so we're going to have a slight change of tack because quantum computing is far more complicated. It was a very short talk. So I'm going to talk about something I do understand, and I'm here to talk about the UK's new national AI service. We call it the very catchy name, the AI Research Resource. For AIR, and this is the UK's first test at standing up large-scale AI infrastructure for researchers, for industry, and for government. This isn't working. Okay, so for the next 20 minutes, I'm just going to provide an overview of the Cambridge Research Computing Service, just to give you some context. I'm going to talk to you about the industrially sponsored. Oh, you're recording? Okay. No problem. No, I'll use. I need another hand otherwise. I have to have my chew thing. I have to have my chew thing. I need this, and then I've got a problem. Okay. So I'm going to cover the Cambridge Zettascale Lab, which is an industrial collaboration around some technology development we do. I'll do a brief overview of AIR and then a deep dive on Dawn, which is our supercomputer in the AIR program, and then I'll talk about a CHPC Dawn collaboration. Okay, so just a brief factoids on the Cambridge Research Computing Service. We started 18 years ago, actually just 1 year before the CHPC, I believe. At that time, we were just a relatively small kind of university HPC service. Over those last 18 years, we've kind of grown to be one of the UK's kind of major national HPC centres. We serve a kind of a large cross-domain user community of around 3,500 active users on the system. That cohort obviously changes because we have a lot of PhD students that come through the system and then move off. Over the last 7 years, interesting. Over the last 7 years, we've provided about 48% of the UK's total top 500 performance. I found if you read all the top 500 spreadsheets into ChatGPT, it can do really good analysis for you. It's a good toy. We have quite a strange business model where we run as a cost center, so we charge stakeholders for usage. We have a number of large national stakeholders. These kind of logos are there. So we pool their investment and we have rolling upgrades, and we provide a shared infrastructure for all those stakeholders to use. We have quite a large kind of self-sufficient in-house technology team. We do all our system design, system deployment, kind of implementation, system support, and user support within inside that one team. So we normally work in collaboration with the vendor, and we build the system ourselves instead of relying on the vendor to support it. We do have a strong commercial supply chain partnership model. That's really important for us. We derive revenue from our supply chain. We derive technology development through co-design with our supply chain, and we actually do outreach through our supply chain's customers in terms of getting impact. Okay, and we have a long-standing and highly productive collaboration and friendship with the CHPC. This started right back in 2007. We've kind of grown up together, and we did bilateral technology exchange and service model development and a whole host of collaborative activities. is one of our best collaborations, I think, that we've managed to develop over the years. So just some brief facts. We provide national and local HPC services to Cambridge, but most of my effort is national. Only 10% of our resources is turned internally to the university. We do service provision and technology development. We have around £100 million of equipment in operation at the moment. That was the data center when we opened it. Actually, Happy attended the opening, do you remember? It was all empty and clean and tidy like that back then. It's completely full now. We have 40 staff today, rising to 50 over the next year. We have 1.8 megawatts of power and cooling. We have around 30 petaflops of double precision performance today. We have around 3,000 Dell servers, a mix of x86 GPUs from Intel and NVIDIA. We have around 45 petabytes of storage, again disk, NVMe and tape. And we have a secure computing trusted research environment for medical data. Just a brief slide on the Zettascale lab. This is a $10 million, 6-year program. We just signed off the final 2 years funding now, the next 2 years. It's an industrial partnership, mainly funded through Dell and Intel, for the co-design, development and testing of all kinds of HPC AI solutions. It's really about democratizing these technologies by increasing their functionality, making them more flexible, making them more efficient, increasing accessibility, lowering cost. Well, this thing's got a life of its own. I didn't even touch it. Anyway, and how the lab works is we try to make this kind of virtuous circle, co-design circle, where we get a fusion of science use cases. We need the scientists to tell us what they need, what problems. This is really quite strange. You get the scientists to tell us what their problems they have. We use our service provider knowledge. We get technology inputs from the vendor. We put all that into a kind of a pot with critical mass and skills and infrastructure, and we create kind of proof of concepts where we go through this innovation cycle of requirements capture, deployment, evaluation, and we iterate. Okay, it's a basic principle. We have a whole load of different themes in the lab. There are around 15 engineers now employed in this lab. We have a whole load of themes. The red ones are the themes that we've used to build. This slide wants me to move faster. It's telling me, speed up. You're too slow. I'm bored with that slide. The red ones are the technology threads that have actually been used to create Dawn. Okay, so one API Center of Excellence is Intel's programming environment for their GPUs. We've done a lot of work on the middleware, accessibility and tools. Obviously, storage for AI systems is difficult, so we've had to use some specialist NVMe platforms, and we want to secure that data. So all those themes have been used. In fact, the Dawn is run out of this lab, mostly because the hardware costs for Dawn were covered by Dell and Intel was part of the lab. So Intel funded that whole supercomputer capital cost themselves as part of the lab activities. So I'm only going to talk about one theme in a little bit of detail, which is our middleware stack. We use OpenStack for our middleware. Traditionally, with more traditional static middleware layers, you would have different software platforms for each of these types of activity. With OpenStack, it allows us to build a shared, configurable, heterogeneous hardware base that we control via OpenStack APIs. And then with Ansible, we can have software-defined research platforms that sit on top of that hardware. So that enables us to have a very flexible middleware layer that can morph between different research platforms kind of on demand. We work with a company in the UK called Stack HPC, and we've produced a kind of a full stack science platform now. We get funding from UKRI, from the SKA, from industry and from AIR. This is being wrapped up into a community cloud project sponsored by UKRI, and it really revolutionizes, I think, the flexibility and end-user functionality of HPC systems. It revolutionizes how we can serve up resources to customers in ways they want, more like the commercial cloud. This OpenStack controls all of our infrastructure in one large bare metal cloud. It's gaining traction within large HPC centers. I think you need a certain critical mass before this becomes practical. I think Happy you run the same OpenStack from the same company here in South Africa. Yeah, so that's part of our collaboration. It's now running here on some of Happy's systems. See, I don't have to touch it. It does it on demand. It's reading my mind. It's AI, man. This thing is, it hasn't changed there. It's changed here. This is bizarre. Okay, so now we switch gears, talk about air. So air represents a £300 million investment in two of the UK's largest supercomputers, designed and configured especially for AI workloads. It's kickstarting the UK's next generation of AI infrastructure. If there is any money coming, we don't know about the next generation. We expect there will be. And it's providing large-scale AI capacity, as I've said, for research, for industry, and also for government. Obviously, the UK government sits on a large wealth of what we call sovereign UK data. There's lots of data assets that the government wish to derive value from, and they want to use these machines to do that. So there's two systems, one at the University of Bristol called Isambard AI, and our system in Cambridge called Dawn. The first phase of Isambard is now up and running. It's 168 Grace hoppers. Phase 2 should be in the second half of 25. That'll be another 5,000 Grace hoppers. So that's a huge GPU system. Our system is 1,000 Intel GPUs. And I think the government is now about to issue a call or expression of interest for Dawn, I believe, soon. And there will be some details in there of the type of workloads they're expecting. I think they are widening it to simulation workload now as well, which is interesting. I'll speed up. This is what it looks like. That is a Dawn Blade. It's a 2U server with the x86 on the top and the water-cooled GPUs underneath. We have 256 of these nodes. Each node has 4 GPUs, 2 CPUs, 1 terabyte of RAM, 4 local NVMe drives, and 4 HDR 200 cards. Because I wanted the message rate, not the bandwidth, so we doubled the number of cards and half the rate, so we get the message rate. So this should be really scalable once it's working properly, because it's all kind of first generation and quite difficult. It's water cooled. It consumes a megawatt of power, which means it needs a megawatt of cold water coming through. All this looks like that was all retrofitted in our machine room. So we retrofitted 2 megawatts of liquid cooling. We have 240 liters of flow per minute running through those servers. As I say, it's a first generation liquid cooled Dell server. Dell had never done a server like this before. They developed it with us, so there were obvious leak issues. It's Intel's first generation GPU, so there are obvious many issues there. And of course, it's the first IB cluster with Intel GPUs because their large system in the States uses HPE Slingshot, exactly. So there's lots of firsts here, which means the system integration was quite tricky. It took 8 weeks from purchase order to delivery, and then 3 weeks from delivery to top 500, because you can do that in a dirty way. But then stabilizing the system ready for production has taken much longer after that. This is the network cabinet. It's a thing of beauty in my mind. We have 32 top-of-rack switches, 100 L2 and L3 switches in the core. We have 34 kilometers of cables. There's 1,000 ports of 200 gigabit fully non-blocking, which is actually 100 terabits a second of cross-sectional bandwidth in that core. And I asked ChatGPT, and it told me it's equivalent to 1.5 million households' internet traffic going full burst, which is quite interesting. And around 65,000 laptops if you include their GPUs. So it's a reasonably powerful system. So just as importantly, actually more importantly than the hardware really, is how we make this system available to users. What is the user environment for an HPC, for an AI machine? It's different to the user environment for an HPC system. We don't just want to give them Slurm and say, here it is, take it or leave it. We want to try to make this a more useful AI system. We're doing this work in collaboration with our colleagues in Bristol and Sadaf Alam. And we tried to come up with these different use cases. So user stories, you might just want to run a big MPI job in batch. You may want to run a Jupyter notebook to visualize some data. You might just be working on your laptop where most of the AI developers are, and you want a bigger laptop. You might want to run a workshop or a class. You might want to run a production service on a Kubernetes-style infrastructure. Or you may want something secure. So we have all of those kind of use cases. And our OpenStack environment can be used to provide those. And so when we look at what we're presenting, we have an OpenStack cloud-native supercomputer at the base. We can have multi-tenanted partitions, and then we can pivot between two usage modes. We have a Kubernetes environment for Jupyter Hub, Kubeflow, or custom platforms that you run on the Kubernetes. We can interface that through notebooks and dashboards. We can have just a shell, a shell access with batch jobs, runtime containers or VS Code. Again, you can interface that through Open on Demand, a graphical interface, or just a script. And of course, you have all your AI environments. Intel now work with Hugging Face, and there's a lot of AI model containers that you can just run on there. And then you can build out kind of AI and MLOps platforms and frameworks on top of that. So an AI supercomputer is a little bit different. We're creating a single pane of glass across Cambridge and Bristol using technology the product's called Waldor. It's from an Estonian company called OpenNode. It's what you will log on through if you use any of the Euro HPC machines up at Lumi, and others use this technology. It's open source. We use that to have a single sign-on. And of course, there are various workflows that will be instantiated by Waldor, depending whether you're a shell or you're Kubernetes. We're developing that now. It's a really interesting project. It's funded by Excalibur. And I think this is going to have a lot of impact in the UK as we think about how we move to a federated DRI across multiple sites. So Dawn is in early science mode. It's been in early science mode for the last year. We had 140 users, 65 different projects, and we were quite surprised how easy it is to get AI working because you just use PyTorch. Simulations obviously are a bit more tricky because you need to port them with one API, but AI codes port quite easily. This is a spread of the domains, and this is the spread of the AI models, and this is really important for government because government are fixated on LLMs, and the LLM use is just this. Most of the AI models are not LLMs. Yes, this is quite useful for policymakers. Scientific AI is a lot more than LLMs. Just some taste of the projects. We're working with British Antarctic Survey, using Dawn to generate models of sea ice. Very classical model of using Dawn to detect cancers in CT scans. This is shifting gears. This is a simulation. This was done by our colleagues at UKAEA, some quantum Monte Carlo. Scales very well. The interesting thing for me here is this difference between the current class CPU and the GPU. We're seeing a 12 times speed up, which is actually quite interesting because it's 12 times the performance, only 3 times the energy, which is actually nice, and 12 times the speed up and probably about 3 times the cost, 4 times the cost. So, it works out much more cost effective running on GPU, and it saves a lot of energy. So the last slide, actually we have had some of Happy's users on the system in a small scale while we were in early science mode. Now we're going into full service early in the new year. We can increase the amount of resources we can give to HAPPY's users. So I think we're going to talk about you running an expression of interest to get access on the system for simulation and for AI, and we'd really like to see a lot more of CHPC users on the system in the coming year. And that's it.
Thank you very much to all our speakers. It was fantastic for Francesco to give us an introduction to quantum computing and take us to the roadmap of the developments, the challenges and opportunities facing our continent and South Africa. It was great for Scott to give us a deep dive into some chemical structure and how we look at the thermodynamic properties using different to gate-based quantum computers to quantum annealers on D-Wave. And finally for Paul, just to give us an overview of the hardware and infrastructure that they have available in the UK. So for us, there's lessons learned and best practice to adopt. And there's also, as Dr. Stoll is arranging, an opportunity for collaboration. I mean, Francesco will be happy to hear that the Dawn cluster is this massive GPU cluster, and for us to be running our gate-based simulations on that will be a fantastic opportunity. So the floor is open for any questions from the audience to our three speakers. But before that, let's give them, all our speakers, one more round of applause. Thank you.
Thank you very much for the great presentation. I had a question for Francesco. I agree with you with saying that if Africa misses the train of the quantum revolution as well as the AI, it will be really 50 years behind. I would argue even more than 50 years. But it really presents a great opportunity, and I totally also agree. But I was just wondering how you can, if you could expand a little bit more on how Africa can really leapfrog in light of the cost associated with quantum hardware, and then even the access to it, and then the dollar amount associated with it. I was just trying to picture myself, is there area you could see where they can hang on to basically create that uniqueness, or maybe to create some strength, or if you can just elaborate a little bit more.
You know, I think in the opening session, I don't remember who, probably all the speakers mentioned collaboration. yeah, that's the only chance we have. Yeah, and collaboration in science means open science. So we really need to not only work together but share also what we produce. Yeah, and you know, and in the times of AI, open science doesn't mean only open source. It means also, on the one side, open access. Yeah, that's why there are global efforts to set up an open quantum institute so that everybody has in principle access. But in the specific context of AI, it also means open weights. Yeah, so if we join forces to develop our own LLMs, yeah, we need to share the weights. Yeah, because not everybody will be able to buy 100,000 GPUs like Elon Musk does when he wakes up in the right mode. Yeah. So we need to first have a joint effort to have, I don't know, yesterday evening at the dinner I joked with Mervyn, please buy us 100,000 GPUs. Yeah? Maybe 5,000 is more than enough for our purposes. Yeah? But we need a collective effort to have it. Yeah? Because otherwise we just speak about fourth industrial revolution, we don't do it. Yeah? We really need the tools to do it. And for quantum computing, it's the same. Yeah? We need access to quantum computing hardware. Yeah? Why we can leapfrog is because, you know, in Africa we have problems that other continents maybe don't have. Yeah? We developed this very fancy and useful online banking app. Yeah? It started with Vodafone, with M-Pesa, and all those kind of things, yeah? That other continents don't use. Yeah? So we have our own problems. We need to come up with our own solutions, yeah? And that allows us to leapfrog. And then maybe the UK start using M-Pesa, yeah? Because they're envious that we can do payments cheaply and quickly and so on and so forth. Yeah? Things like that. Yeah? And you know, I mentioned climate change. If we don't start collecting our own data, we won't be able to use the fancy AI model that allows you to do weather and climate change prediction much faster using AI, yeah? Because we don't have the data. So it's all, you know, it's all connected, yeah? And we need just to start somewhere, yeah? Yeah. Sorry, I could go on for hours.
Thank you, Francesco.
Well, thank you for the talk. I have two questions. Like the first one, I just wanted to ask Prof. Francesco. I think the key, perhaps for Africa, is for IP collaboration across maybe academic institutions. And I just wanted to find out the state of actually institutions collaborating in that field, as well as the access to IP from like the other continents. Like you did say that they've already kind of closing up those kind of avenues. So what's your insight with regards to that? And then I also wanted to ask with regards to the UK AI presentation is, what are the checks and balances with regards to the public? And because we've seen like some governments sometimes abuse the power when they have like that kind of infrastructure. So are there any kind of like checks and balances and also protection measures so that there's no abuse? Thank you.
You know, I'm glad you ask again about collaboration, yeah, because my main job is that I'm the director of the National Institute for Theoretical and Computational Sciences, yeah, which is an institute in charge of 8 disciplines: theoretical physics, astrophysics, mathematics, statistics, data science, quantitative finance, quantitative biology and bioinformatics, and climate change modeling. Yeah? And I want these 8 disciplines to work together, to collaborate. Yeah? So that's why I sort of don't like speaking about interdisciplinary, transdisciplinary, multidisciplinary. That's not enough. Yeah? I like speaking of pandisciplinary. Yeah? And in my definition of pandisciplinary is that what is important is the challenge. Yeah? The disciplines, I don't care. Yeah, I want my guys to solve problems. Yeah? How they do it doesn't matter. Yeah? There is no better discipline. I know some theoretical physicists think Big Bang Theory like the TV show, yeah, that they know everything better, but that's of course not the case. Yeah? So the important thing is solve the problem, yeah? And work together to solve the problem. If you don't work together and don't solve the problem, you won't get any research resource from me. That's how, you know, academics are like cats. Yeah? If you want to come together at the same point, you need to feed them. Yeah? And the food is just research funds. Yeah? So that's how you start collaborations. Yeah? In a very practical way.
I call my Cambridge academics cats because they fight each other. That's the other side. Yeah, AI safety is actually a really interesting topic. The UK government has spent a lot of time investing into AI safety research, their institutes. It's not my field. I stand up the infrastructure, but there are a lot of people thinking about guardrails and safety, and especially with the government data sets, especially when you look at health and tax records and all this data that they have on the population. How can they derive valuable, you know, knowledge from that data, but not have data leakage out and be, you know, giving things away that they shouldn't? There's a whole institute, several institutes in the UK looking at this. I can send you some links if you're interested.
have a question for Prof. Francesco. You mentioned we are in the NICS, in the area of noise intermediate computing system. Do you think that it's possible to have a free noise computing system? Or we must to develop some kind of noise engineering or noise robust system? So how do you see the future in terms of noise processing?
I have a plane to catch at 2. Yeah. No, we have this noisy intermediate state quantum computer, but we have also evidence now essentially since the last couple of months that some quantum computing hardware companies can produce error-free logical qubits. Yeah? And one company claims to have 28, another claims to have 40. Yeah? And that's fantastic news, yeah? Because if next year they have 100, yeah? With 100 qubits error-free, you can do lots of things, yeah? Because it's 2 to the power of 100 without any noise. Yeah? And these are, I think, very encouraging signs that that we are getting there. Yeah? When we can, the noise intermediate state quantum computer you can just use for training purposes. Yeah? So far, nobody has solved a problem that one of these gentlemen here can't solve on their hardware. Yeah? With the error-free ones, with the logical qubits, once we have 50, 100 logical qubits, then you can really start doing serious stuff. Yeah?
Are there any further questions for our panel? Okay, I guess they can adjourn for lunch. Please, let's thank our speakers once again. Thank you everyone for joining the session.
Good afternoon, colleagues. Welcome back to our second session for quantum computing track. My name is Lihlonolo Mongalo. I will be your chair for this session. Let's welcome our first speaker for this session, Rose. Thank you. Over to you, Rose.
Thank you. Hi, everyone. My name is Hilary Rose Medifa, PhD student from the University of UKZN under the supervision of Professor Thomas Conrad. Today, I'm going to talk about my research work entitled Solving a Quadratic Optimization Problem Using Amplitude Encoding. This presentation will be done following the outline. I'm going to first introduce and then present the methods that we are using, present some of the results that we have, and conclude. To begin, quantum computers are electronic devices that processes, stores, and communicate information with respect to making use of quantum physics laws. Optimization problems can be formulated as maximizing the profit of a business or minimizing their cost. So suppose that we want to optimize a problem described by 100,000 variables. On a classical computer that uses bits, we might use up to a billion number of bits to solve that problem. Meanwhile, on a quantum computer with only 17 qubits and making use of amplitude encoding, the work is done and very faster. So our problem is to find the best variables that minimize the quadratic cost function as applicable to industrial production line and logistics. Like the big goal that we want to do is to kind of optimize the production line of the German industry, the German technology industry, ZF. They are dealing with cars and things like that. So in order to solve this problem, we have to describe and implement the quantum gradient descent algorithm based on amplitude encoding. Actually, there are numerous work that have been carried on quantum gradient descent. For instance, Ruben Strauss et al. In 2019 introduced the first quantum gradient descent algorithm with Newton's method based on amplitude encoding, and they showed that their algorithm is achieving polylogarithmic scaling in the solution dimension and exponential scaling in the number of iterations. Later on in 2020, Kerenidis developed a quantum gradient descent algorithm for the system of for the least square problem and linear system that reduces the quantum random access memory usage by only storing a tiny portion of the data at a time. In 2022, Liang et al. Proposed a quantum gradient descent algorithm based on linear combination of unitaries to efficiently solve linear system of equations. Sheng et al. Also in 2024 developed a quantum gradient descent method for VQE, where they mainly focus on calculating the gradient of the cost function, and they use that as the optimizer for VQE, making the VQE to be purely quantum. So concerning our methods, we are using amplitude encoding, as I earlier said. It's just a technique of encoding the information into the amplitude of a quantum state as represented in equation. As represented here in equation 1, where this is the capital N is the total number of amplitude of variable that we have, and this relation needs to be satisfied. So classically, the gradient descent is described as in this equation, and quantum mechanically, we have it in this equation, where this is the updated state and this is the current state, with alpha the step size. So the objective function that we want to minimize is described as in equation 4, and the gradient of this cost function is given in equation 5. To implement now the full algorithm, we use two procedures. One procedure is the one that helps us to encode the whole thing, this iterative formula that brings the old state this to this new state, and the other procedure is the one implementing the gradient, which is given in equation 5. And how do we implement this gradient? We use two subroutines. We use two algorithms, one that is going to help us implement this matrix vector multiplication, and the other one that is going to help us add the B vector onto the A side to get the full gradient. So the algorithm for the matrix vector multiplication is as follows. We start with two registers. I call it X and Y, where the X register is the eigenvalue register and the Y register is the solution register. We put the X register into superposition, and then we prepare the Y register in our initial gates, into our initial state. Then, as for the phase estimation, we need to choose our unitary such that it respects this equation, and then apply it k time controlled by the X register to the Y register. And then after that, we apply the quantum Fourier transform inverse and get this equation, where the Bj here in the X registers are represented in this form, where phi j is the eigenvalues of the A matrix, of this A. And we can see that these eigenvalues are encoded into the basis, and what we want to do is to move these eigenvalues from the basis to the amplitude. How do we do it? We add an additional qubit register that we are going to rotate condition on the qubit of the X register. And this is what we have. So when we rotate it, we have this, and we project onto the one state of the Z register and choose our angle theta such that sine theta is equal to the phi j, which is the eigenvalue. So we can see that it moves from the basis to the eigenvalue have been shifted from the basis. The eigenvalues are in front here, and now what we have to do is just uncompute the quantum Fourier transform and the control unitaries, and we get our matrix vector multiplication. So how do we do now to get the full gradient? As I said earlier, I will describe the vector addition technique that we use. So in order to do the gradient, we need to add another qubit register P1, where we control the P1 register. We rotate the P1 register with respect to the angle gamma, choosing this way. So when we rotate, we have a cosine theta 0 and a sine theta 1. We condition on it being to 1, and then we apply B. So we can already see that we have a B1 side. And then, given that our AX matrix multiplication was with Z equals 1, we need to first flip the Z register and put it to 1. Then from there, we condition on the P1, and then after that, we flip the P1 register as well. We flip the P1 register so the 0 becomes 1 and the 1 becomes 0. Then we condition when it is 1, we put the AX, so we can have now the AX on one side and the B on the other side. And then after, we just need to flip it back and then apply Hadamard and get our AX plus B on the 0 vector for P1, and then we project onto it and we have the gradient that we want. So what I was mathematically saying is represented here in this circuit. So this is a circuit representation of the gradient where we can see all the operations. And when we transpile this circuit with respect to this basis gauge, we saw that it's giving us 1,072 layers. So we had to look for ways to kind of reduce these layers, because 1,072 layers is too much for a quantum computer, given that they are too noisy, and the error per layer gate is 10 to the minus 3, which is too much. So we had to add additional qubits again, which is not also very good, because the more the qubits, the more the noise. But here we can see that we add an additional qubit to kind of perform multiple control operations, and we succeeded in reducing these layers from 1,072 to 285, which is actually a good thing as well. So for our results, we use matrices A that are symmetric and positive definite. Why? Because we want to ensure that they have Because we want to ensure that they have a global minimum, making them to, we want to ensure that they are converging to a global minimum, avoiding the barren plateau scenarios. And the vector B are as well chosen in such a way that we have normalized solution, because we are dealing with quantum states. So making use of the same, because we want to get our updated state, which is the current state minus a step size times the gradient, we still have to use the same vector addition technique that I showed before. We just have to add another auxiliary qubit, and then rotate that auxiliary qubit with a negative angle, so that we can have one part minus another part, and then perform the same operations to get our one step. So this is the circuit representation of one step on the quantum computer. Our intention was to perform all the steps fully on the quantum computer, but we can see that because with this step we already have 500 layers. So if we want to iterate, if maybe the problem is taking, let's say, 10 iterations, then 10 iterations is 10 times 500, which is already too much of layers. So what we did at this level is that we measure one step and we classically iterate it to see what the solution will give. And then these are the results that we got when we are evaluating 2 variable problems, that is 1 qubit, because we did for 2 variable problem and for 3 variable problem. So these graphs represent the cost function evaluation versus the number of iterations, and for 3 different matrices with a step size of 0,3 and initial input to be kept 0. So we see that to be kept 1. So we see that for this case, the optimal solution is approximately around 16, 17. Same here, and here is around 10, 11 for the noiseless simulator. We also simulated it onto the noisy simulator, and these are what we get. Here we saw that the solution is approximately 25. Here as well, and here is going to approximately 16, 17. And on the real quantum computer, we did this one case of the matrix, and this is the result that we saw. We see how the quantum computer is too noisy and what it is doing, and actually it is here, but it's not the optimal solution. So maybe if we added more iterations, we could reach to the optimal solution on the quantum computer. So we can see that the noisy simulator that mimics the quantum computer kind of is requiring lots of iteration as compared to the free simulator. And these are the results that we also get when simulating with 8 variable problem, that is 3 qubits, and we can draw the same conclusion for 8. What we are actually doing now is for 32 variable problem. We already had one case that is working, then we are still kind of working on it. So we can say that our algorithm is effective and efficient in the sense that it takes very small iteration to reach the minimum as compared to existing hybrid methods like the variational quantum, eigensolver, VQLS, QAOA. This successful convergence highlights the capability of quantum algorithms to tackle optimization problems. We also saw that noisy simulators generally require more iteration. They reach slightly off solutions and increase gradients, emphasizing the importance of noise management for optimization tasks on quantum simulators. So potential mitigation strategies such as using noise reduction technique or error correction could enhance solution accurately. This work, if we have logical qubits, a good amount of logical qubit and access to quantum computers, then we can say that this work can revolutionize industry by providing them with quicker solutions to their real-world problem. Thank you.
Thanks, Rose, for the interesting talk. Colleagues, do we have questions for Rose? Rose, looks like you don't have any questions, so thank you. Our next speaker is Dr. Isaac. Isaac, over to you.
I want to remove this one. Thank you.
Videos. Yeah, I do. So I'm going to just connect the audio.
As long as it doesn't have audio. You can use it to do that.
Yeah, I'll just plug it in. Oh shit, can I remove that? Cool. Let's do this. This first. But it's not. I'm gonna do it. It's clicking. It's not clicking. I don't know why this doesn't want to work with the back. I'll just click. Yeah. Okay. Cool, brother. Okay, so afternoon everyone. So I'm Dr. Isaac Nape from the School of Physics at WITS, and today I'll be talking about quantum computing as a tool for photonics. So I think let's treat it more like a tutorial, and I'll try to walk you through how we can simulate some effects in optics using quantum computers. So this work is also funded by the South African Quantum Technology Initiative. I think Professor Francesco spoke about it briefly. And it's also part of the research that I do at the Structured Light Laboratory, which is run by Professor Andrew Forbes, myself, and Dr. Angela Dudley at WITS. Okay, so what do we do in our lab? Basically, we work in quantum optics, quantum and classical optics, and we look at the engineering of quantum states of light for quantum communications. We look at quantum cryptography as well. We look at state transfer over long distances, so quantum teleportation using spatial states of light. We also look at quantum imaging. So if you have entangled photons, how can you utilize them, or rather use them as a resource for imaging? And we've recently been looking at quantum computing using lasers. So everything that I'll be talking about is based on, we call it structured light. So basically, if you look here, you see many patterns, all which are distinguishable from each other. And this is basically what you get if you had a laser beam and you modulated it using devices that come out of your projectors. those are called spatial light modulators. So they allow you to control or to distort the spatial structure of light. And we can do this with full control. What's interesting is these modes are actually mode solutions for the classical Helmholtz equation. And even if you quantize the field equations from classical optics, you find that at the single photon level, these mode solutions still persist. So if I have a single photon and I measured it over time, I'd also still see these patterns. What's interesting is this equation that I've written here, I mean, this is for classical optics. It bears a resemblance to the Schrödinger equation. And the idea is that instead of having time as my, on this left-hand side of the equation, I instead have propagation. So Z, which is propagation, acts like time in quantum mechanics for Schrödinger's equation. And so you also notice I have something that encodes a potential-like object. In optics, this would be the properties of the medium that my laser field propagates through. And the idea is, given this analogy between the quantum and classical equations for light, I would like to be able to start simulating some of the effects that we see in photonics using quantum computers. So what do I mean by that? I would like to find a way to embed the features of my photonic state or system into a quantum computer and apply operations on them and then be able to obtain an output from a quantum computer that tells me something about how these laser fields behave. And obviously we need a machine to do that, which will be our quantum computer. And this quantum computer will basically be composed of many different operations that act on the quantum states that I'll be preparing. And once I send these states in, I can read out the data. And this must follow all the rules of computing, particularly the Church-Turing principle, which is the fact that you can compose computational computations by just using simple logic gate operations. So, I mean, just to step back a little bit, quantum computers have been said to be, in future, maybe allow us to do physical simulations, which is what we want to do here. You can also start solving systems of linear equations using these quantum computers, and it seems like you can do it in logarithmic time. And you can also start showing that you can start training machine learning models in order to be able to, perhaps, for example, here, use them for classification. And if you're interested, I think Professor Francesco presented earlier, but he has a nice textbook on machine learning using quantum computers. So anyway, the main focus here is, again, to get back to how do we encode information into these quantum computers for the objective that I defined. So for some of you that haven't been at the workshop and weren't here earlier, I mean, a quantum computer operates on binary states of information, but not in the classical sense. In fact, if I looked at this switch here, it has the state 0 or 1. But in quantum mechanics, I can have a system that can occupy both states, 0 and 1 simultaneously. This is just superposition. And you can also think of it as a particle that can occupy more than a single path simultaneously. And this would mean that the particle is both in path 0 and path 1. So these are just ideas to visualize the superposition principle. And usually you'd find that you can scale the contributions of this 0 and 1 state. Again, just to go through the basics, we parameterize these states on the Bloch sphere. If you're at the North Pole, you have this state vector here, which is just a 2-element vector. And then I can construct one that is orthogonal to it, which is at the South Pole. So these are my 2 states that I encode information into. And these we'll call the logical basis. And from that, I can then be able to produce any other possible state by controlling these parameters theta and chi. So basically, these here allow me to determine any state on this parameter space. And then from these, I can construct other states, such as these superposition states. I think you've already seen one of them. and another set here, and these are basically eigenstates of the Pauli matrices. Okay, now, I mean, if you only have a single particle, you can only encode 2 states of information. And if I have to think of the states as paths, if I'm trying to maybe solve a problem where I'm going through a maze, having to access only 2 states of information at a time might not make me efficient if I'm trying to find my path out of this maze. Maybe increase the number of particles. So for example, if I have 2 particles, then I have 4 possible states of information that I can represent using these particles. And so then you'll find that I'll be more efficient at finding my way out of this maze. So here you'll see that from having 1 particle, I only had 2 states of information. Increasing the particles increases the states of information by around 2 to the power of n. And so ideally what you want to do is to have as many of these particles as possible. And these particles are these qubits that everyone talks about. And the idea is that once we have enough qubits to perform computations, we will be able to encode matrix and vector operations at a very large scale. And then once I have these qubits, I want to perform operations on them. One of the sets I can apply are just rotations on the Hilbert space that I showed you. So if I had my qubit on one of the poles of the Hilbert space, I can move it around, for example, by applying the Rx gate, Ry gate, and Rz gate. These allow me to have rotations on the X, Y, and Z axis of this Hilbert space. But I can also build another universal set that allows me to move around anywhere on this Hilbert space. And these are namely the Hadamard gate, the phase gate, and the T gate. So, I mean, it's not enough to have single qubit gate operations. You usually want to be able to also perform multi-qubit gate operations. And this is because if we want to encode information in 2 to the n element vectors, then we should be able to construct operators on n-dimensional, d-dimensional Hilbert spaces. So it turns out that, well, you can choose combinations of single qubit quantum gates as well as 2 qubit quantum gates. So here's an example of a universal set that you can do that with here. So that would be the 3 gates that I showed you before, and including the control NOT gate. So then the idea is, if we want to study the evolution of a quantum system, then we find a way to encode the features of the problem into a quantum computer, maybe using rotation gates. And from that, we can tune the parameters of these rotation gates and then be able to maybe visualize the evolution of our quantum states. And on the quantum computer, this is precisely what we want to do. So now, getting back to our problem, now that we know how quantum computers can be programmed to simulate evolution of quantum states, why is it of interest to us in photonics? Well, in photonics, for example, if I'm doing biological imaging, I would usually be sending photons or light beams into maybe tissue, but these might destroy the integrity of the laser beam. Maybe for fiber optics, but maybe there might be losses in these channels, or the fields themselves change due to perturbations. Satellite communications, we know that the atmosphere can destroy the amplitude and phase of optical fields, and there are many other applications. So, for example, here's an image of a laser beam that we sent out across a 350-meter channel, and you see that the laser beam is busy wobbling around. And what's actually happening here is the refractive index of the atmosphere, because of temperature fluctuations and pressure, are causing the laser beam to change in time. So an example of this is, I can think of my laser beam as some initial state that was prepared, and then as it propagates through the medium, it actually gets distorted. And the time evolution operator that we use is very similar to the one that we have in quantum mechanics. Okay, and what you see is that we're exponentiating an operator here. The first part looks at the paraxial propagation, so this would be like the free Hamiltonian of the system. And then the second part encodes the phase perturbation, which would be my turbulence in this case. And so, I mean, you see that this has a structure that is similar to the time evolution operator in quantum mechanics. Again, if I want to be able to encode these operators onto the quantum computer, I need to find a way to efficiently decompose this Hamiltonian into quantum gates that are easily easy to compose on the quantum computer. So before you do that, firstly notice that sometimes the two Hamiltonians that make up the time evolution operator are not necessarily commuting. So then you can't just factorize this exponential. Most people apply the Suzuki-Trotter formula, and this basically just means that Seth Lloyd famously actually calls this time slicing. You can apply two operations in sequence in order to be able to get the full evolution operator. And you will notice that while the operators F and U int are actually repeating in sequence. And we can increase the precision of these operators by just increasing the number of times that we repeat them. And so all we're doing here is we're applying the free Hamiltonian part as a unitary operator represented by F naught and the interaction with the atmosphere as U int. Okay, so getting back to the optics problem that we developed, we can apply this time slicing operation. And in fact, you can do this with second order precision, and you'd find that, well, all you have to do to actually model the turbulence here is you just need to apply the free space propagation, then perturb the state, and then apply free space propagation again. So this allows you to actually simulate the effects of propagating through free space. And this is actually called the split step method. In optics, this is actually a well-known technique. And so basically, you propagate, and then you apply your perturbation, and then after that, you propagate again, and you get your solution. Now, in order to encode this, it turns out that propagation in Fourier optics can just be modeled using Fourier transforms. And this is because if you look at the Fresnel diffraction equation and even the Fraunhofer diffraction equation, which describes how light propagates in the near field and very far away from the source, you can simply write it down as simple Fourier transforms. So we basically need to be able to apply these Fourier transforms. And in terms of the position basis, so point-wise on the optical field, the perturbation itself is just a diagonal operator. And if you look at the complexity of these two operations, on a classical computer, to apply the discrete Fourier transform, which is what you would usually use if you were doing these simulations on your computer, you find that the complexity is actually exponential. And similarly, I mean, if you move to a quantum computer, instead of applying DFT, we would be applying the quantum Fourier transform. And you see that the complexity scales quadratically. So you do far better in terms of complexity by using the quantum computer for these kind of simulations. And then also to encode a simple diagonal operator that encodes the perturbations that we want to encode here, you see that to do this on a classical computer is also requires, well, there's exponential complexity, whereas on a quantum computer, if I'm using phase gates at best, I'd get quadratic complexity. So still, again, I do much better on a quantum computer. So there has been some nice work where they focused on propagating optical fields, but using a quantum computer. And as you can see, the circuit architecture just requires a layer that applies the quantum Fourier transform. So this models the free space propagation. Then you might encode the transfer operator. This would be similar to just encoding an impulse function that represents your system. And then you would apply the inverse quantum Fourier transform again, which would be what I showed you before. propagate, perturbation, propagate. So this here somehow allows you to model that. In this paper, however, they did it using just free space diffraction. So they were just simulating how a laser beam propagates from the source plane up to some other location. So we haven't started yet with these simulations. However, we've been formulating this problem, and we've been doing some of the theory. So far, we've been doing some numerical tests where we're looking at using this procedure to actually compute the eigenmodes of some given perturbation. So what do I mean by eigenmodes? I mean that we're trying to find the optical modes that are invariant to some of the perturbations. So in this first article here, we've been looking at a modal approach. So instead of looking at how every point in space so instead of looking at how the fields propagate in space, by looking at how each pixel or every point diffracts in space, we instead have a modal description of these fields and then study how the modes are busy interacting during propagation. So we want to then take this model and then also apply it on the quantum computer. And recently, we've been able to produce results that shows that it is in principle possible to actually find these eigenmodes, except the student who did this CADE would tell you that it takes him days to actually calculate these eigenmodes. Later on, I think you'll hear from Hadrian about how we're now trying to actually engineer these perturbations so that you can start being able to do things like classifying optical modes using these perturbations. So what we do is we play the game of finding the perturbations that we can allow to interact with our optical fields so that our optical fields are able to be detected. In fact, this is a new emerging field which is actually called diffractive neural networks, because basically you're building a classifier in an all-optical setting. And then Moisey will also later talk about how we use these quantum algorithms to actually be able to identify quantum states. So not just model them, but how do we get classical data that someone measured? Maybe this is from a quantum entanglement experiment. You just give him those measurements, and then he runs a quantum search algorithm, which then returns the state. And with that, I'd like to thank my collaborators and most of our funders. And yeah, I'm open to questions.
Thank you, Isaac, for the interesting talk. Colleagues, do we have questions for Isaac? Do we have questions for Isaac? No, we don't have any questions for you. Our next... Oh, we have one.
On the slide where you were comparing classical and quantum computing efficiencies, for the you were showing the after you separate the simulation into two stages, repeated two stages, and said that you were saying that the classical, and this is where I didn't quite get. You were saying that it is the diagonal matrix.
Yeah.
When you're saying the diagonal matrix, what mathematically, what is that operation?
So by diagonal, I mean, because so far I'm treating the optical field as a vector, right? I've embedded the optical field into a single vector. To encode the perturbation from turbulence, it's just a diagonal operator that we apply. And it's actually, on the optical field, these are just phases that you encode. So if I wanted to encode this onto the quantum computer, I need to take this diagonal operator and then find a representation for it in terms of my 2-qubit quantum gates. So if I used, let's say, a rotation gates, phase gates, then on a quantum computer, this would just take cubic complexity, but on a classical computer, to encode a diagonal matrix, I think might be 2 to the n operations. Where n is, so here n is just, it's representing the number of qubits that I would use classically so the number of qubits that I would use on a quantum computer to encode my state vector. Yeah. Yeah. I guess this is a comment on the number of operations needed. Okay.
Thank you, Isaac. Our next speaker is Paula. Over to you, Paula.
Okay, hi everyone, my name is Paula. I am postdoctoral research at the Structure-like Laboratory as a professor and as Dr. Isaac as well. So today I'm going to talk a little bit about our recent research. So let me start my presentation asking a question for you. So when I ask you what quantum means for you, what is the first word that comes in your minds? Okay, we are a small group, so you can say to me, like, are you? What is the thing that comes in your mind when you're thinking quantum?
For heaven's sake, it's discrete. It's according to Max Planck.
Yeah.
Discrete.
Okay, thank you.
What's a quant?
Well, okay, yeah, it's a question. Well, when I think in quantum, as someone here say, in the quantum movies, you think in scale, right? Maybe you're going to difference this scale, the microscopic world and the microscopic world. Some people can think in probability or randomness of the quantum physics, quantum mechanics. Some people can think in entanglement, right? But as Professor says here, the word was introduced for Max Planck as the notion of the minimum amount of quantity that it can exist, right? So quantum physics is in our physics world, I can say that, for almost 100 years. So since Max Planck started with and his scientists start with the idea of quantum physics, we have a lot of advances in the quantum world. So we start with the quantum pre-mysteries, where in the lab, physicists are busy to try and understand what is the way to describe these phenomena, for example, the black body radiation or the photoelectric effect. But in order to understand this theory, they start building these quantum foundations, right? Describe a theory to describe these kind of phenomena and try to understand something that we call the quantum phenomena, right? Quantum phenomena like entanglement, or superposition, quantum tunneling, and etc. And using these ingredients, we are going to be able to build some kind of theories calling, for example, quantum information theory. That is my background in the quantum information theoretician. Well, and here we're discussing about the quantum computing, but we know as well for the talks that we have before and everything that we listen today, we have quantum communication, quantum teleportation, and all these kind of quantum theories. Well, one of the main ingredients that we have for the quantum thank you, for the quantum physics is the quantum superposition. So starting with his thought experiment with the Schrödinger car, showing the main idea of the superposition and giving us a big problem to deal, that is quantum measurement theory, we know that at the quantum level, some kind of quantum particle could be in two states, right? Only when we observe, when we do a measurement, we are going to know the exact state of the system. And another ingredient that we are very interested in the quantum world is the quantum entanglement. So we're here talking about the quantum entanglement. We discussed how if you are measure one particle in some point, it's going to affect the state of the entangled particle in some kind of distance. But the important thing here, when we talk about quantum entanglement, it is this property, this correlation happens no locality, yeah, so it is a non-local effect, and includes as well the superposition. Well, here you can see, for example, this is a picture of two spins entangled, and here, for example, if you make this measurement in one of the particles, you know the state instantly of the other particle, or the entangled particle here. And here you can see, for example, this is the step up that creating two photons entangled in polarization. But, nowadays we are far from the idea that the quantum physics is only a theoretical framework, right? As I said before, it started in the lab, and now it's like we have some kind of evidence. We have evidence that actually it could be a very powerful tool. And Professor Petruccioni mentioned, well, it's part of the second revolution, like he said. Well, so we know that entanglement particles, especially the entangled photons, is the topic that this gentleman won the Nobel Prize in 2022, and specifically for performing experiments with entangled photons and showing the violation of Abel inequalities and being the pioneers of quantum information science. But here, you must asking like, but what is an entangled photon, right? So these entangled photons can be created in the lab. You send ultraviolet photon here. This photon here is interacting with a nonlinear medium, and then after these processes, you are going to have these two twins entangled photons. So this process to obtain these entangled photons here is called spontaneous parametrical Dom conversion. So you have some kind of the specific nonlinear medium here, you send your single photon, and at the end of the process, you obtain an entangled pair of photons. So let me stop a little bit to explain, because I am saying to you, okay, I am sending a photon interacting with the nonlinear crystal and it's entangled, but what exactly we are going to entangle, right? It's like a broad definition of what they're going to entangle. But let me explain a little bit about the degrees of freedom of the light. So you're going to understand what we are entangling in the lab. So when we have a light, a field of light, we have this kind of structure. We are going to have, we can describe the light in terms of the transverse structure. So we are going to describe this light in terms of the phase, of the intensity. We can describe the light in terms of the frequency. It's nothing more than the color that your light have. And you can describe in terms of the path that your light is taking, or in terms of the polarization. So these degrees of freedom of the light behaves like a fundamental alphabet for describe the state of the light or the state of the photon. So here we have, for example, this state of the photon. It could be described in terms of polarization, temporal evolution, or spatial localization. when we describe the state of the photon of the light in terms of these degrees of freedom, we're dealing with something that Dr. Isaac mentioned previously, structured light. So the structured light is nothing more like tailoring the degrees of freedom of the light in order to perform some kind of processes that we want to do. So here we have a beautiful patterns creating with the structured light, and in the laboratory of Professor Andrew Forbes and Dr. Isaac Nape, they are busy building, as he mentioned before, these different structures of light with different kind of purposes. So it is far from these beautiful patterns. We always we create these structures in the lab, and we use for different purposes. In my talk, I'm going to take you specifically how we want to create. We use these kind of patterns in order to create quantum information processes. So as the previous speaker mentioned, we have in the classical computers, we know that we defined the information in terms of zeros and ones, or binary bits. But if we go to the quantum world, we can use the superposition principle in order to define something called qubit, right? But if you think in terms of the light, we can do the same thing using, for example, the different degrees of freedom of the light. In this case here, we use polarization, and we build an exactly parallel between the polarization and the qubit or Bloch sphere that Dr. Isaac mentioned previously. But in this case, polarization is only referring to two degrees, right? You have a right, left, horizontal, vertical. But you can go to further dimensions. You can as well encode your information in temporal degrees of freedom or transverse degrees of freedom, or also as well called pixel basis. So as mentioned before, this is a higher dimensional basis, so you can encode high dimensional databases here. As well, you can use, for example, this high-dimensional discrete position basis, as I mentioned before. So, for example, you have this complex structure, and you can describe this complex structure in terms of the position basis or other kind of basis, more sophisticated, if I can say that, like at this Laguerre-Gauss basis. But my talk here is going to refer to the pixel basis. So we can explore the quantum properties using quantum structured light. As far until now, I tell you, okay, there are something called quantum. I can use quantum. I can encode my qubits in the degrees of freedom of the light, right? But now I'm going to focus specifically in the position correlations. So as I mentioned before, after the nonlinear processes here, you obtain two entangled photons, these twin photons, and they are going to be especially localized. So if you send one of these photons in this path, they are going to be especially correlate in another position, in a different position. So let me explain this thing here. So we are going to have spatial correlations. So if we have entangled photons here, and we are going to send these entangled photons, they are going to follow in this path here. One of them is going to interact with this measurement device. They are going to be correlated in the other twin photon, is going to be especially correlated. So in that way, you can build the structure of your image of object, and you are going to build the coincidence image in this way here. Okay, these kind of special correlations are used for something that is well known in optics. It's called ghost imaging. So for ghost imaging, you are going to send one of the photons to interact with an object, and in the other arm, in the other path, you are going to be able to detect the image. So in the part that I have the camera, I'm going to be able to reconstruct my image or my object. So here, the main aim of the ghost imaging is be able to reconstruct an object with no interaction. So that is the takeaway of this part here. So the object, in this case, for example, could be any kind of image here, could be described in terms of the pixel basis here, but it could be used any kind of the degrees of freedom or basis that I tell you before. In this way, the image that we have here, for example, can be described in terms of these amplitudes times these, we call them random masks, in order to reconstruct the image. But the main idea of my talk on our research is, well, we know well how ghost imaging works, but we can make some kind of data searching using this tool. Well, in order to describe this, let me tell you a little bit about the searching algorithms. So searching is something natural in the humans, right? We always searching something. We always, mainly in these days, we always go to the Google and search something, some kind of information. But for example, there are some kind of specific problems, like a traveling salesman problem, that are looking for ways to search in an efficient way. So one of the algorithms that it was proposed to increase the speed or searching with more effective ways was proposed by Grover. So this is one of the famous quantum algorithms. So he and his work, he said that if you use quantum algorithms, the number of operations that you're going to perform is going to be less, quite less if your database is bigger, compared with the classical algorithms. So Grover and Dutch show so far the most relevant algorithms in the quantum level. So let me explain the quantum Grover algorithm. So he proposed that we have a database. In the database, you have something that you're looking for. So here, I show you, you have this image here, and actually I like so much to do this thing. You must find a rabbit in the middle of the cat. So this is something that you start to looking for, and I tell you where is the rabbit. I don't know if someone is going to be able to find it. But okay, the process of the aim of the Grover algorithm is to identify the object that you're looking for, inverse his probability or its probability, and then at the end of the process make some kind of amplification in order to find the object that you're looking for. Well, these processes as well can be seen like geometrical processes. So you can define, for example, the state that you're looking for. And notice here I can define the state like a quantum state. Yeah, where we are going to define the good state, the good subspace, the object that we're looking for, and the bad subspace, the rest of the information. Thank you. So when we have here, this is the object plus the noisy information. If we apply the Grover operator several times, our aim is to go to the good space, find the information that we are going to looking for. And now considering, obviously, the noisy that is something that we don't want. Okay? So we perform It was some kind of very nice conversation that Isaac was having in the lab and seeing how this could be related with our optical setups. And we see mathematically they are very equivalent. Actually, they are the same. So we can perform this Grover algorithm using the ghost imaging processes. So here I show you how you can make the parallel between both. So initially, you have the database and the noise. So we encode here the database and the noise at the Grover algorithm. And then we are going to perform the oracle or the oracle query from the Grover algorithm. And our experiment is going to be the object that is going to be encoded in one of the paths. And at the end, you have the measurement and the amplification. So here, I show you the parallel between both. So in the optical experiment, we have the initialization. And here in this database, we have all the information that is in our disposition. Here in the oracle, we encode and inverse the object that we're looking for. And at the end, we are going to measure or detect our image. This is the experimental setup. So we created a single entangled photons. One of the twins interact with this mask. One of the other twins interact with the object. And then at the end of the process, we are made the reconstruction by coincidence. So let me show you the results that we have, because I think I am running of the time. So here we encode a simple Gaussian distribution. This is the theoretical prediction. This is the experimental result that we measure actually in the lab. And then we increase our resolution. So we increase the number of pixels at 64 experimentally. Then we increase for different of the dimensions, 96 and 128. So we can imagine it that we have our Hilbert space here, with database is inside of this Hilbert space, and we are going to encode something like that. We have this imaging here, noisy subspace, and the good subspace here. So if we perform the Grover processes, we find that encoding a small database, we can separate the bad subspace and the object nicely. Here is going to be a little bit difficult because then you have all this information around, so the bad subspace is going to be a little bit tricky. So experimentally, you can see this in the results here. So we are encoding here our object. Our object is going to be this here. So if we encode the object and the noise in this relationship here, we are going to be able to make the reconstruction. But if the database is bigger, our experimental results are a little bit restricted. So that's all, and thank you so much. I think I overstepped 1 minute. And thank you so much for the opportunity to be here, for the organizers invite us to be part of the conference, and yeah, that's all.
Thank you, Paula.
Thank you.
Do we have questions for Paula?
Yeah.
Okay, yeah. Thank you for the talk. It was a nice talk. I'm a novice in quantum photonics and things like that, so I just want to know, throughout the first part of your presentation, you were talking about structured light. How is it different from light? Like, why structure?
It's like a way to say it's not different. It's when you structure the light to play with the light, right? So you can use these special modulars of light to create, for example, the basis that you're going to use in quantum mechanics. So So instead to use the 0-1 computational basis, you can use the pixel basis, for example, or you can use Laguerre-Gaud basis. So using this device, you can send the light and make control of your light, your beam, or your photon to behave in the way that you want.
Okay, so if I understand that the structure there is just for you to control the lights.
If some say yes, I don't say only just because it's a little bit complicated, yeah. But yes, yes. This is the way that you're going to give the light is, okay, I know now my photon is going to interact with this pixel, I know it's going to do this thing, right? So you have a certain control over the being of the photon, yeah. Thank you so much.
Thank you, Paula. Our next speaker is Moezi and Henry. Over to you.
All right, good afternoon, everyone. My name is Hadrian Bezaidnote. This is Moezi Kone. We are both master's students, first year and second year respectively. We work within the Structured Light Laboratory that operates within the University of Witwatersrand. Today I'll be sharing with you some techniques on training phase masks for diffractive neural networks for the first part of the talk, and then I'll hand over to Moezi for the second part. So to give a brief overview of neural networks are multi-layered systems. They consist of 3 types of layers: an input layer, hidden layers, and output layer. Each layer consists of multiple neurons, and each neuron in the layers are connected by some sort of weighting. And these weightings are each individual to each, or unique to each connection. Using this sort of infrastructure, we can take an input state, we can modulate it in some way using the hidden layers, and we can map it onto some sort of output to do various types of processing. The same sort of system can be implemented optically using a diffractive neural network, where these layers of diffraction act as our hidden layers. We see that if we take a coherent light source, which means just a flat plane wave, which acts as like a blank canvas for encoding on, and we interact it with a diffraction plane, at each point that it interacts, it forms these spherical waves, which as they travel to the next plane, these spherical waves interact with one another, forming an interference pattern on the next plane. That interference pattern is then modulated once more, doing the same thing, and it is transferred through the system to some sort of output plane. We can then intelligently model these diffraction planes to make sure that our input layers correctly map to some sort of spot on an output layer. So how does this actually of use? It has multiple uses, anywhere from image recognition to simulating quantum processes, and even quantum cryptography can be done with this simple architecture. So I mentioned that we design these diffractive layers, but how do we actually do that? We use a spatial light modulator, which has been mentioned before. A spatial light modulator is just like your normal LCD screens with pixels that you can switch on and off by applying some sort of voltage. I then mentioned that we have a plane wave that we interact with these diffraction layers, and what happens here is that by bouncing this plane wave off of this LCD screen, we can actually encode some sort of pattern onto the front of this wave. Now, taking note that 2 properties of light is actually the amplitude and the phase. The amplitude is how bright the light is, and the phase is how delayed each point in this grid is comparative to one another, which creates some sort of profile which acts as a fingerprint for the wave. We note that our elements on our SLM are actually encoded in the exact same way, where we can do amplitude modulation to adjust the brightness of the light, or we can apply a phase modulation which adjusts the different delays in the pixels. These phases are actually encoded in a range from 0 to 255 in an 8-bit format. And using this, we can actually take advantage of a range of different values and not only be limited to switching pixels on and off. By doing phase modulation, this is also less lossy, and it can provide a platform for more complex beam shaping, so we can get those nice patterns that you've seen before. But I say we train these diffractive layers generally to model these neural networks. And the general approach to this is by training each pixel individually. And one can imagine that if we have a HD screen, since this is a regular LCD screen, it quickly leads to a large number of parameters that need to be trained if you're doing this pixel by pixel. So how do we actually remedy this problem? We can switch from the pixel basis to what is known as the modal basis. What I mean by this is that we have a set of nonlinear functions in optics called the Zernike polynomials, and these can actually be used to model the neurons in a neural network since they require a nonlinear activation function. These are generally used to describe distortions in light, so aberrations, how an optical field is manipulated by atmospheric turbulence or any sort of distorting medium. These polynomials can actually be added together with some sort of weighting that is analogous to the weightings in a neural network. This allows us to construct a phase screen which we can use as our hidden layers to modulate these waves by distorting them in some specified manner. To take a look at the advantages of our approach, we can compare to the pixel basis approach. To be fair to people, we note that we actually encode multiple phase screens on one SLM device, so we don't use the full amount of pixels, but larger, smaller areas. But even doing so, comparing to a range of different papers for similar systems that compute similar tasks, we see that even a small amount of pixels for each phase screen leads to a large amount of trainable parameters. Using our approach, we found that we can have similar results using only 63 Zernike polynomials. This is amazing because the less parameters you need to be training can lead to reduced training time. We can also take advantage of high-resolution solutions since we can increase and decrease the size of these Zernike polynomials without actually having to increase the amount of parameters that need to be trained. Since these activation functions are actually physics-based, it offers potential for simulating physical processes, which will be very useful for obvious reasons. And it is actually adaptable to environmental changes for multiple reasons, including the decreased number of trainable parameters, so you can make quick changes to these systems. And since these fields are naturally used to describe things such as turbulence, we can actually use them to counteract this sort of turbulence for disturbances in our optical fields. How we actually implement this is the image you've seen before in Dr. Nape's slide. We construct multiple phase screens on one SLM device. We can then take an input wave. Here's a Laguerre Gaussian mode. It looks like a little donut in its intensity profile. And in its phase profile, it actually varies from negative pi to pi as it goes from purple to white. So we see this unique spiraling pattern. Then by bouncing this mode off of the screen, we can actually map it into a desired channel. So here we've set up 4 channels, and our target channel is this first spot. This can be extended to multiple modes, and by bouncing these modes off of the exact same phase screens, we can map each mode into a specified channel. By doing this, we can actually characterize these modes. So if we see a click or a spot of light in our desired channel, we can actually know which mode was sent into this system. So taking a deeper look at the system, we see we have our input modes where the individual modes here, L1 and L-1, which are different indices for our Laguerre-Gaussian modes, they have an identical intensity profile, except one spirals from purple to white, one spirals from white to purple. This is information that is encoded in the phase of the light, which is actually what we'll be modulating. We see that we send these input modes through the system. We use what is called what I call an imperfect imaging system, which keeps the beam size constant, but it actually scrambles the phase. This acts as a sort of separating tool for our modes, since some modes may have an overlap, meaning the same phase is present on the same spot, which means our system might map it to the same location, and we want to be mapping it to these different channels. So by scrambling the phase, we can actually separate these modes, and we can map them into their individual channels. And here you see the Laguerre-Gaussian basis being mapped onto the logical basis. And we see a clear neural network structure with our input layer, our hidden layer, and our output layer. Extending this characterization problem into a more computational set, we see that by describing input vectors as Gaussian mode arrays, which are just spots of light with different phase that represent these different values, 1 and -1 down here, we can map these channels onto their various spots, which again maps a superposition basis onto a logical basis, or 1, 1 onto 1, 0, and 1, -1 onto 0, 1. We can then note that if we perform this sort of mapping, we have performed the same operation as a Hadamard gate would have, which is a common operation in quantum computing. And by mapping different operators in the same way, we can start performing optical computing operations using light. So to look at how we actually train this sort of process, we set up a cost function and we set up an error threshold, which acts as a stopping criteria. We then take our input states, which I have explained previously, and we map it onto these phase masks using these bounces. We then take a projective measurement. So we, after putting this through the state, we check if the spot has been mapped onto the spot that we wanted. So you see here in the cost function, psi would be what we are observing from our mapping, and then phi would be what we actually want from our mapping. So we then ask ourselves if all the states have been measured. If they haven't, then we go to the next input and we do the same measurement. Once all the states have been measured, we can calculate the average of the difference between what we have and what we expect, and this will be our cost function. We can then ask if our cost function is, at the current step, is smaller than our optimum cost function, where the first step will always be accepted as an original guess, and then from then on, the steps will be compared to that original guess to start the minimization process. If we find a better step or a better solution for our weightings, we can set the current weightings and the current error to the optimum error. Or the optimum error to the current error, rather. And we can ask if the current error has reached our error threshold. If we got lucky and did it in the first step, we can immediately exit our loop. If we haven't, then we go and change these weightings again, and we do more projective measurements, and we continue the process. Now, if at a step, the current step is not better than the optimum step, we can bypass this whole thing, retrain the weightings, and go again. This optimization procedure, for interest's sake, was implemented using MATLAB. So here we can see a simulation as the solved modes train to their desired channels. At the top rows, we see the intensity profiles, and at the bottom rows, we see the phase profiles. We can see that the intensity profiles begin identical, and as they travel from plane to plane, they split in a unique way, and then they're eventually mapped onto the desired output channel. Now I say they're mapped onto the desired output channel, but how do we actually know this? Well, we can actually extract the intensities in each channel, and we can form an output vector that looks like this. We can then combine these output vectors into a matrix where a perfect mapping into each channel will give us an identity matrix, which is just this diagonal of ones. We can then compare the matrix we solve to an identity matrix to compute a quantity called the fidelity. So what is fidelity? Well, fidelity is the measurement of what light actually mapped into the correct channel that we specified previously, whilst the efficiency is a measure of how much light made it into the channels in comparison to how much light was scattered around. Now we can see as the training process continues, our phase screens modulate themselves, our cost function decreases, and at the very same time our efficiency increases and our fidelity increases alongside it. Now here we can see the crosstalk matrix that was constructed from these output channels that were measured. And doing this sort of analysis, we can confirm that our training procedure is actually working the way we want it to. This idea can be extended to multiple dimensions, as I have shown you previously, where we can map our various input channels into their output channels based on some sort of target function. And we can construct the identity matrix or a crosstalk matrix, which we're trying to solve for the identity matrix. And doing so, we can actually analyze and see that our mapping was performed successfully. So by increasing the amount of modes that we're actually encoding in this process, we can increase the alphabet. So we move beyond just ones and zeros processing, and we can start describing more complex, higher dimensional computations. So on that note, I will hand over to my colleague Moezi, and he will take you through some photonic state reconstruction.
Okay. Oh, hi, everyone. I'm Moezi, and I'll be presenting our work on photonic state reconstruction on a quantum computer. Many speakers have introduced what we do in our lab. So what we basically do is we tailor light or shape light in different degrees of freedom, both at a classical level and at quantum level. Most of the speakers have spoken about this spatial degree of freedom, that is how light is in space, but you also do it in the time domain, and also in the frequency, that is the color of light that you see. And often tomography is a useful process that we use to characterize our state at a quantum level. Assuming that you would have built a quantum experiment and you want to test actually, does it perform the way in which I would expect? In the next slide, I'm going to introduce you to this problem of tomography. So imagine that you are trying to reconstruct some object from its projections. So you have some light which shines on this object, and you can only see its projections. So the process of tomography is actually reconstructing this object from these projections that you have, and it often requires some computation. But in the lab, our objects are quantum states that live in some multi-dimensional Bloch sphere. And this is a typical experiment that we would perform. So you shine some laser beam into some nonlinear crystal, and then you generate some entangled photons. And we use SLM to perform these projection measurements, which are similar to those light beams. And this is the measurement results that you'd often get in the lab. Now, the process of tomography is trying to move from this measurement to describing to obtaining the density matrix, which would describe this quantum state of these entangled photons. If you are familiar with these states, so this would be some maximally entangled Bell state. So mathematically, this process of tomography can be written as this system of linear equations. So you have some projections and some measurements that you get from the lab, and the goal is often to reconstruct this matrix, which tells you about the quantum state that you'll get from your experiment. So there are traditional techniques that have been used to, that can be used to solve this system of linear equations. So the first one is just by brute force. So you find the inverse of this matrix, which you get from your set of projections that you apply on your measurement. And the second one is the maximum likelihood estimation. So what this process entails is that you often have some, so the goal is to maximize some probability distribution of your measurements given some guess that you make given these projections. And it turns out because we make some independent measurements, and this problem can be reduced to some least squares fitting problem. So in essence, so you just have some measurements, and then you make guesses of this density matrix such that you fit some model into these measurements. So the question we ask is, can we use quantum computers to solve this, these systems of linear equations? So can we actually reconstruct quantum states given some measurements that we get from the lab, and then input them into the quantum computer such that we can reconstruct our density matrix? It turns out that Seth Lloyd and his colleagues have proposed some quantum algorithm which promises some advantage, that is some speed up over classical methods. But the problem with this algorithm is that if you look too deep, you'd find that it's computationally expensive. If you look at the circuit depth, that is the number of unitary layers that can be executed in parallel, it's quite long. So it would actually be hard to execute this process within the lifetime of current qubit processors. Now the question is, how can we best utilize the current hardware, which is noisy and has a limited number of qubits? So a few years ago, Peruso proposed variational quantum algorithms whereby you take your problem and then you split it into into the classical part and some quantum part. So a classical computer, which is your local processor, would be responsible for this part, and while you leave some part of the problem to the quantum computer. So on the classical part, you often make some guesses, and then so the goal is often to reach some solution which solves your problem. And then on the quantum computer, you ask whether you've reached your state or not, and then you'd continue making guesses on the classical part until you've reached some convergence on your quantum computer. So your quantum computer would effectively be computing some cost function to your problem. And then if you have not converged to this solution, then you'd make new guesses on the classical part until you converge to your solution. So it's an iterative algorithm. So we iterate these parameters of our state, which we call theta, which tell us where we are on this block sphere until we've reached our solution. And this entire process can be summarized into this single quantum circuit, where you prepare some answers on your classical computer, and then you then send the circuit into this into the quantum part. So this entire middle section would be designated to the quantum processor, where you'd compute these cost functions, where they would tell you whether you've solved your problem or not, and then you iteratively update these parameters until you reach convergence. And then the question is, how do we map our original state tomography problem into a quantum computer? So we take our least squares problem, and then we phrase it as a cubo problem, which is some quadratic unconstrained binary optimization problem. So it's quadratic from this power of 2, and it's not constrained. And we use this, we convert it into this binary because of the current hardware, and we encode our information into the actual registers of our quantum processors, of our qubit states. So what we do then is we perform some transformations of our variable, which are elements of our density matrix, into spin variables. And then we then construct this Ising spin model. And now our problem changes into, so we've translated our problem into this mathematical problem, into this physical problem, where we ask, so what is the configuration of these spins that would minimize the energy expectation value of our Hamiltonian? And the idea is that each spin can be mapped onto each qubit on the quantum computer. This is actually the qubit topology of one of IBM's quantum processing units. And how we actually rotate these states is through gates. So we would iteratively change these parameters of these gates, which are rotation gates. And then we can also apply some entangling operations, such as the C0, which allows the interaction between the qubits. For instance, here, this C0 would cause some interaction between this first bit, sorry, this first qubit and the second one. So here I show that we're able to reconstruct 2D biphoton state, and these are actually simulated measurements. And over here I show our training procedure until convergence. Ideally, our expectation value reaches close to 0, and this is a bit string distribution that we get from the quantum computer, displaying all these possible solutions. And from there, we extract the bit string with the highest count, and then from there, we reshape it into this 4x4 matrix, which tells us the density matrix that we reconstruct from the quantum computer. And here we actually extend it to real experimental data. So what you'll notice, the difference between this data, this is the simulated data with no crosstalk, and then over here we apply it on some noisy data, and surprisingly the quantum computer is still able to predict our state. Now the question is, can we scale it up from just 2D biphoton states to higher dimensional states? So over here, I've shown the results where we try to extend it from just 2D states to 3-dimensional states. But then here you see that we're able to predict 77 out of 81 bit values. But then we see that our count is less than 2%, which is not enough. And then the question is, how can we scale it? I mean, would quantum computers then be useful to, for large-scale VGE problems? Actually, recently, it has been shown that by IBM that with error mitigation techniques that quantum computers can actually evaluate the noisy cost functions better than brute force techniques. And this era is called the era of quantum utility. So we believe that with these error mitigation techniques, once you start incorporating them in our scheme, we we should be able to scale it up further to H1 qubits. And with that, I would like to thank everyone, and especially our team from VETS, which is the Structured Light Lab. And lastly, here are our two papers, which I co-authored with Adrian, which are similar to the work that he presented earlier. The first one is on using this variational approach on a photonic system, whereby we were learning some unitary operators. And then the second one is on using the same system of SLMs, trying to do some quantum computations. Thank you. There's a question over there.
So thank you for the great presentation. My question goes to Hadrian. I'm more curious about how quantum cryptography would employ your architecture.
So how quantum cryptography would employ our architecture?
Yeah, the architecture with the hidden and the initial and the output.
So by using this sort of characterization technique, you can define certain mappings that can be used for processes like quantum key distribution. If you correctly define your bases, you can switch between them to do certain, put certain signals in, take certain measurements. So how it would actually be applied physically would still need to be designed, that sort of thing, like, implemented in the infrastructure. But these base-like processes can be used for a wide variety of quantum processes. So signal processing or quantum communication would be my immediate thought in how it would be applied.
Do we have any questions? Oh.
Hi, mine is a stupid one. Can you just go back to the last slide? Yes. Not that one. The very last slide that you showed.
Next.
Yes. Those two images, what do they stand for?
These are QR codes. So if you take out your phone, go onto your camera, you can actually scan these. It will take you directly to our paper. Yeah.
Any more questions? Okay.
I mean, just a small point, Moezi. I think you sort of switched the, just go back to your variational circuit.
It doesn't, can you? Oh, okay.
Your variational circuit, yeah. Back. Here, I think, I mean, in case there's people who actually want to do this, the first layer is where the quantum computer does the state query, right? The ansatz is on the quantum computer, and the estimator is done classically, right? This is a crucial point. I think you kind of swap them,
okay.
Just for anyone in the audience that's, interested.
Yeah, last question for Moezi. No last, sorry, my last question. Yeah, Moezi, when you make these variational quantum algorithms and you make these hybrid algorithms, so technically what you do? You go to your computer, your classical computer, and put your data, and then how you perform the quantum classical thing?
Oh, okay. So
Yeah. Thank you.
what you do on your local computer is that you sit down and you write down these parameterized circuits, and then from there you send them to the IBM cloud where you can send your job, and then you give it your Hamiltonian variable. And so what it does is that it takes this second and your Hamiltonian, and then it computes this expectation value. And then it would then output it. And then on your local computer, this optimizer that you set up, then it will take these expectation values and then ask, okay, have we reached the lowest value yet? And then it would iteratively then continue giving new guesses until you've computed the lowest expectation value. Yeah. So you just set in some seconds, form your local computer, and then the quantum computer would then evaluate this expectation value.
I think we don't have any question. Colleagues, this is the end of our session. Thank you to all the speakers. I think we have a tea break downstairs. Thank you.